afternoon, everyone. Sorry, so I'm starting a little late, or sorry, I got time, but got everything set up a little late because OBS was not working. Um, and um, it's hot and sticky here, so I'm going to be a little out of it. Also jet lagged. So we'll see. We'll see how well this goes. As always, if there are questions, please don't hesitate to ask them as we go. The chat's open. I'll check the Patreon for questions at the end if anyone's preferring to ask questions there in the comments. And if there's anything weird with the sound or anything, let me know, and I'll try to address that. I already got a message in chat from Anurag. Thanks, real kind post there. So one of the challenging things with a lot of the analytical stuff is that in my opinion, so I'm coming from a practical perspective, right? I started as a scientist, and so my goal is more to develop practical models that have real applicability. Now, part of that is this kind of give and tug between the complexity of the model needed in a given application and the computational tools we have available to us. And something like Hamiltonian Monte Carlo really allows us to expand the scope of things. But there's still constraints. I mean, the hidden Markov model chapter is one of them. I was just having a conversation with someone recently about marginalization and how it's, they were saying, well, isn't this really like not a general tool because there's a lot of discrete systems we can't marginalize over? And my response is like, yeah, it's not a general tool. We can only marginalize certain systems, and we do the best we can with those systems, right? So, and the fact that HMMs are useful is because we can run the forward and backward algorithms, because we can analytically marginalize out these particular conditional dependencies, which is not in general true of a lot of these systems, right? You can kind of tweak and perturb the HMM, and it becomes something that's no longer analytically tractable. So yeah, we're always kind of living on that knife edge, right? Things like Gaussian processes, Brownian bridges that you mentioned, kind of are on that knife edge. And I think where it comes to me with SDEs is that SDEs have a lot of really nice theoretical properties. There's a lot of work on dynamical systems that shows that when you add a little bit of stochasticity, right, add kind of a driving Brownian motion to a chaotic dynamical system, the noise can stabilize the dynamics. And this is one argument for why a lot of kind of n-body systems in astronomy, even though they're formally chaotic, they kind of appear to be much more stable than they might, and because there's a lot of these kind of low-level behaviors that appear to be noise or can be modeled with noise. But the tools we have right now that are available to actually work with SDEs are quite limited, right? The Euler-Maruyama discretizations are quite crude, and I think they're really not up to snuff for working with actual dynamical systems. It's really just these kind of like linear, very close to linear systems. So I don't know. So it's always a give and take. I try to find the opportunities where I can. I think there's a lot of kind of analytical systems that are very popular in theoretical math that I don't think have great practical applicability. And that's one reason why I might not consider them, or it might just be that I haven't had time to look at them. So if there's particular things that you're interested in, or really anyone's interested in, don't ever hesitate to reach out. It can be like, hey, I like these kind of systems, I like these kind of systems, and that can help motivate future work with the acknowledgement that, or recognition that only so much time in a given day, and we do what we can. So yeah, thanks again for the kind words. Hey JD, thanks for confirming that sounds good. All right, so let's go through this. The first section here is the part that I'm kind of most hesitant on, and I think at some point I'm going to try to clean this up. I don't know when I'll get to it. Ideally, I'd do it before I release this publicly, but not a lot of time. the reason I'm a little hesitant about this presentation is as I kind of present it as observations first, and then the states are really defined by those observations. And as we see later on in the chapter, this isn't necessarily the best way of kind of presenting these systems, because we can have, for example, multiple observations per state, different numbers of observations per state, and so on. So really, I think it's best to introduce, and in hindsight, after having written the full chapter, I think it's going to be more useful to present the states first as these kind of individual contexts where data is generated from this mixture of data generating processes, and then kind of construct everything from there, right? So this I index comes first, and then the data is generated within those individual contexts, and that allows us to kind of more generally and more naturally think about the heterogeneity across these observations, right? So I mentioned it here that, you know, I can be discrete for some states and continuous for others, or it can have varying numbers of dimensions. So I mention it here, but I think pedagogically it might be easier to start with states, and that will then make it more natural for this heterogeneity to be reasonable across the observations. Of course, if people have perspectives or opinions, you know, always happy to hear what might be more compelling to different readers. So we start with the observations, recognize that there might be heterogeneity in them. In particular, the observational models, you might note, I'm allowing to vary by state. So a lot of times with the HMMs, they're presented as if it's just like the same thing repeated over and over again, and that's often how it's modeled. But the actual math works out that the observational models themselves can be quite different. All that really matters is it's the same number of components. That's the key. And really that can also itself be loosened pretty easily. So there's a lot of flexibility here in this construction. It's one of the reasons why it's so useful in practice, because we can manipulate it into a lot of different systems. It's not the rigidity of that we see in other kind of more mathematically well-behaved systems. I'll come to it at the end, but, you know, for example, state space models, the common filter, that can be considered a generalization of a hidden Markov model, but that generalization relies on even more mathematical structure, which makes it even less more narrow in its application. And I think that's where, you know, common filters kind of, to me, they take that step into being just not quite general enough for a lot of cases. You know, they're great for the systems they were designed for, where you're observing a dynamical system over very short increments of time. But in a lot of more modern, more contemporary, more realistic scientific analyses, we don't often have that control, and so that linearity becomes a real obstruction. Anyways, so we have these repeated states, and we can think about these states as assignment variables, similar to what we did in a regular mixture model. So in the mixture modeling chapter, we just had this one state, if you will, and that state is determined by this variable z, which quantifies or specifies the particular component that that state takes. So what we're doing here is we're repeating these mixture models. Instead of just having one mixture model with one assignment variable, we're having lots of mixture models with different assignment variables. And that sets us up into a joint model like this. So we have our repeated observations. These y variables need not be the same dimension. They need not be scalar, right? Just remember these are just generic variables here. And they all depend on these assignment variables, right? But they depend on them jointly. So the general construction, we're talking about replicating mixture models, is to have this joint model for the z's, for these assignment variables. And to make this a little more compact, because there will be a lot of mathematical derivations here, instead of writing z1 ... zi, y1 ... zi, I'm going to use this notation here, where we use a colon. And this will be very similar to people who might have used, I think R and NumPy both use this convention, where you can do a starting index, ending index, colon, and then it will just give you the vector of elements, vector comprised of the elements with those indices. So again, we can kind of write this joint model using this more compact notation, and that will make some of the equations a little denser, but a little bit more compact on the screen. All right, so we have this joint model here. Now, we've already considered two special cases of this in the mixture modeling chapter. One special case was that all of the component variables were identical to each other. In that case, we get our standard mixture model. We have multiple observations. Each of those observations could come from one of those data generating processes. But they all come from one of those data processes at a time, right? So all the observations are coming from one data generating process or another. Another special case that we considered in the mixture modeling chapter is completely independent assignment variables. And this one's a little bit trickier. What ends up happening here is that each individual observation can come from one of those data generating processes, those component data generating processes, but they need not come from the same component data generating process, right? So we get that kind of admixture. And what happens here is when we try to marginalize out these component variables, we end up getting something that looks very similar to the previous mixture model, just the interpretation's a little bit different. It's no longer the probability of each of the component data generating processes, it's the proportion of observations that came from each of those data generating processes. And again, all of that is done in that mixture modeling chapter. If you haven't seen that, recommend taking a look. So the general challenge here is because these component assignment variables are discrete, we can't really work with them directly. This is just a standard challenge with computational statistics, is that in order to explore probability distribution, we need to use tools like Markov chain Monte Carlo. And while there are generic algorithms, they don't tend to work very well. They don't tend to scale to high-dimensional systems. So we need more information to inform this exploration. On continuous spaces, we can use differential information. We can use gradients to fuel Hamiltonian Monte Carlo. We don't really have an equivalent of that on discrete spaces. And there's a bunch of reasons for this. One reason is that discrete spaces are in some sense more heterogeneous than continuous spaces, right? All continuous spaces have very similar structure to them, and we can exploit that common structure. But each discrete space is kind of unique in its own way. And so any kind of notion of gradient or differential kind of changes as you go from one discrete space to another. And that itself kind of complicates what information might be available. And so you're often kind of led into the situation where you need a bespoke solution, if there is a solution at all. So it really helps the implementation if we can marginalize out those discrete variables. And as we saw in the mixture modeling chapter, we can do that in these two cases. So if all of the component assignment variables are the same, as we see in the top figure, or if they're independent, as we see in the bottom figure, we can marginalize out to discrete states in that case and get to the marginal form of a mixture model. And that allows us to extract information from these mixture models, implement inferences using these scalable tools like Hamiltonian Monte Carlo. But more generally, we can't work with an arbitrary joint distribution. It can just have frustratingly complicated or kind of arbitrarily complicated discrete dependencies and discrete structure, which obstructs any kind of computational tool we might throw down. So we really are limited to these exceptional circumstances where we can marginalize things out. And fortunately, these two cases are not the only two cases. There's one more case that we have the ability to work with analytically. And that is when we have Markovian dependencies between the component assignment variables. So the idea here is that the component variables don't just they're not just like jointly coupled together. Each component variable, each assignment variable only depends on the previous assignment variable in this order. And one of the requirements here is that there is an ordering of these discrete variables, right? There's a notion of Z1 comes first, then Z2, then Z3, ... all the way to Zi. And so it's not just an arbitrary discrete space, right? It's an ordered discrete space. And if we have this kind of particular dependency structure on this ordered discrete space, it turns out it's going to be just enough to allow us to get analytic results out. So our model, under this Markovian assumption, breaks down into something like this. We're going to see this sequential structure. We have the model for the first state, the observations that are drawn from that first state, and then we just proceed forward, taking into account these conditional dependencies of the assignment variables, and then the observations at each state. Now, conditioning this on observations is where things get tough, right? The joint model, as is, where both the z and the y's are just these unbound variables, relatively straightforward. When we want to make inferences for the z's given the y's, that's where problems arise. So in terms of terminology, the two key assumptions that we've made so far is that we don't know what the assignment variables are, and we've assumed that these assignment variables have this Markovian conditional dependence structure, and hence the name hidden Markov model, right? This is one of the cases where the naming's pretty good. Hidden isn't the worst. Markov is a pretty clear description of this dependency structure. We can argue that maybe this isn't precise enough, because the hidden and Markov, they don't necessarily imply the observational structure. And so I think it's not unreasonable to be a little more precise to something like a Markov mixture observational model. Just to kind of emphasize the not just what's happening with the z's, but what's happening with the y's given the z's. But in these days, when you say hidden Markov model, you're not just, even though the name only describes what's happening with the assignment variables, there's an implicit assumption of what's happening with the observations as well. It just kind of become canon, right? The dependencies, conditional dependencies between two neighboring assignment variables are referred to as transition probabilities. And as we'll see later, we can organize these transition probabilities into a matrix, which will be very convenient for implementation. And then, depending upon the nature of these conditional dependencies, we can have kind of further classification of these models. If these transition probabilities are homogeneous, if they're stationary, if they're the same for every pair of neighboring assignment variables, we can refer to a homogeneous hidden Markov model, as opposed to the more general case, where these transition probabilities can vary. It might be referred to a heterogeneous, non-homogeneous, or even just a general hidden Markov model, or just hidden Markov model itself, with homogeneous hidden Markov model being the special case. I should probably also add stationary here. That's another one that you'll often hear. Okay, any questions about the kind of basic structure of an HMM? All right, so we've built up our model, and we still have this discreteness baked into it. So what we really want to do to make this practical is to marginalize out over these discrete states. We want to sum over all zi of these states. Now, naively, this is going to be intractable, right? I mentioned it up here. Right, if you try to sum over all of these zi states, that means we're going to get k terms for every I. We're going to get k times I terms that we have to sum over. That's just going to explode. It's going to be way too fast. Actually, no, sorry. It's worse than that, right? It's k to the I, because you have to choose each state independently of the others. So we get this kind of exponential growth in the number of terms in the sum, which is just not going to be tractable. So our hope is that we can marginalize out the discrete variables like we do in a regular mixture model, a static mixture model. And then construct our inferences for any of the parameters. Afterwards, we can then use Bayes' theorem to try to get back to inferences about these assignment variables. Right, so we want to take the assignment variables, collapse them down to assignment probabilities, and then we can recover everything from there. Now, fortunately, this is possible in this case. but it's not necessarily easy or straightforward. These calculations are pretty brutal. So I mentioned here that kind of encouraging readers to jump ahead. I might want to be a little bit more direct in my language here. These calculations are often misunderstood, and I mean, professional statisticians misunderstand these calculations. There's a lot of people in applied fields who kind of present themselves as stats experts. There are statisticians who are very much stat experts in particular fields who think that hidden Markov models can't be fit with something like Hamiltonian Monte Carlo because of that discrete structure, right? They just don't believe these marginalization is feasible. So I really want to have these calculations here so that if anyone ever runs into somebody who's doubtful, they can say, look, here's math. It's done. It's solved. And I want to use the common notation here that other references don't. So the notation of the references tends to be all over the place. I just want to kind of present them here, reframe them using the notation I'm using so that everything is consistent. But it's definitely here for reference, right? It's like it's this close to being appendix material, but I don't quite think I can put it back there. But it should. This is where it's okay to skip, right? Even if you'll see, there's a few points where I just reference some results and don't try to prove them, because proving the results is a giant pain in the ass. So definitely keep that in mind. And if you're watching this on the VOD, absolutely feel free to jump ahead until we're done with the math here. So the tricky thing about this marginalization is that it's recursive. It's not like an explicit result that we just calculate all at once. It's a result that we're going to have to calculate incrementally. And to see what this recursion is, we can approach it from a few directions. One is just to kind of direct inspection. Take a few cases, notice the pattern, and then continue that pattern. In the second approach, we'll kind of tackle it more directly using some more subtle results from conditional probability theory. Either, this first here is maybe more intuitive or might help build up and prepare for the second one. They're all useful, right? It's just kind of the level of rigor that you're hoping for. So we can notice here, if we start with the first state, marginalizing out that first state is relatively straightforward, right? We just have case states, we sum over those case states, we're done. And if you compare this to the marginalization of a static mixture model, you might notice that some commonalities, right? We have some component probabilities here and here. I can't highlight the component probabilities alone, but you see the P of Z1. And then you have this observational model. Very, very similar. The only real difference is the indexing here to note that this is just the first component variable as opposed to the only component assignment variable. Now things get a little bit trickier when you go to the second state. So we combine everything together, right? And expand out all of the terms. All right. Sorry, I should really say. So we're only really we're expanding out all the terms, but we're going to recombine all the terms that depend on the first state and the first observation. So that gives us that joint model for Z1 and Y1. Now we sum over Z1. And the only kind of subtlety here, only difference from what we had before, is that we have this P of Z2 given Z1 term, right? That transition probability is here. So that's going to make this a little bit less straightforward to sum over. In fact, if we didn't have these transition probabilities, if each assignment variable is independent of each other, we could sum over each of them separately, and that would get us into this K times I calculation, which is much more feasible. It's these transition probabilities that really elevate the cost to that K to the I, that exponential scaling, that makes this intractable. And then, so let's just hypothetically, right, we kind of just sum over that first state, and then we sum over the second state. Now, the thing to note here is that we have another similar form to a static mixture model. We have that second observational model for the second observation. The only difference is that the component probabilities for Z2 are not just given by numbers. They're given by the sum over the joint model for the first state and the transition probability. Right? So as we're summing over these states incrementally, or sequentially, I should say, we're kind of at the end of every summation getting back to this kind of static mixture model-like form. One thing that's getting more complicated is the component probabilities themselves. Right, these have to be derived from the previous summations. Now we go to the third state. And we're going to follow the same pattern that we've done before. So we expand everything out. We sum over the first state and kind of combine all of those terms. And now what's interesting is that after summing over the first state, you have this term in brackets here. Come on, Cordo. Let me... Ugh. Killing me, Cordo. So the last term in brackets in blue here, at the bottom, right, when you kind of don't consider the P3 terms, that term at the bottom is exactly the term that we hit for the summand of the I equals 2 case, right? It's that bottom term there without the sum over Z2. So when we try to sum over the larger model, where we're including more than just the first two states, we're getting this recursion, right? It's already kind of popping up by direct inspection. So this allows us to write the summation, kind of the marginal of the first state of this larger joint model in terms of the lower dimensional joint model, where we only consider the first two states. And that allows us to simplify these component probabilities. So we sum over the second state, and again, you see that mixture model-like form here. Right. So yeah. So we keep summing over things, and again, this kind of form arises where we have the observational model for the last state, and then we have these derived component probabilities that are follow recursively from the first few states, right? So what we're doing here is, instead of trying to tackle marginalization for the full joint model, we kind of recursively built up the component probabilities that are needed by working with just the first state, and then the joint model of the first two states, and the joint model for the first three states, etc. And that allows us to build up these component probabilities for the final state. And then we can sum over those component probabilities to give us the final joint model. So in other words, it's this term here, which again I frustratingly can't highlight. It's the Z3 given Z1 and Z2, right? Those are the derived component probabilities. That's the thing that we can construct recursively. And then once we have that, we just have to combine it with the last observational model to give the joint model for all the observations, and then we can sum over that last state, right? That's the pattern we're going to be exploiting here. And arguably, I could kind of explain this better. This is, will get better as I iterate through the revisions of this chapter. But for example, one thing I'm noticing here is it's really worth emphasizing, right? The term that we're getting out here, right? It's this P of Zi given the previous observations. That's the component probabilities if we're just looking at Zi as the last state. And that motivates why we look at that term in particular. So that's one thing I can make more clear. But the key thing here is, by direct inspection, we're kind of seeing this pattern, and we can just assume that it continues and build an algorithm out of that. Now, if we want it right, so if I want to be able to get to this model here where I have Zi given and the observations up to that point, but I've marginalized out the first I-1 states, I can derive that from the previous joint model, which can be derived from the previous joint model, and so on, right? So I just kind of build this up, until we get to a model that depends on our final state and all of the observations, and then that's just, you know, k terms that we can sum over to get to the full marginal for y1 through yi. Now, if we want to prove this more formally, we need to verify that this inductive step holds more generally. And that's a little challenging. So this is where the real nasty calculations come in that I haven't even attempted to derive. So I'm going to reference Bishop here. I really like Bishop's presentation of hidden Markov models. It's where I first learned about them. I think it's better than most of the other HML references out there. And he references a paper by Mike Jordan and colleagues where they derive all of these necessary properties. He also just kind of lists them, but he kind of discusses various ways that you might calculate them. You can do it by brute force. The Jordan paper and Bishop prefer working with conditional dependency structure. So a lot of the rules that you'll hear in things like a lot of the contemporary causal inference literature with deseparability, which is, you know, related to concepts like backdoors and moderators and things like that. They use those tools to derive some of these properties. But that requires familiarity with deseparation, and that's a whole nother, you know, a bag of worms to deal with. So I'm just going to take some of those properties for granted and kind of sketch out the general calculation. What we want to get at is the model for the ice state and all of the observations up to that ice state. And to do that, we're going to kind of do this recursively. We need to peel off that ice state. We need to get to those first I-1 observations and not just the first ith observations. So to kind of isolate that the previous observations, we peel off a yi, and then we expand the model. So we peel off the yi, and then we kind of do a conditional decomposition. So we have the first I-1 states depending on yi, and then the model for the last state and the last observation. Just got a basic conditional probability here. And then taking that joint model for Zi and yi and expanding that as well. Now, this is our first conditional dependence result that I'm just appealing to Bishop and all the properties discussed there. The first I-1 observations are conditionally independent of the ith observation, which makes sense, right? The things that happened previously can't be influenced by what happens afterwards. Assuming we're conditioning on Zi. So what's happening is that the last state between the ith observation and the previous observations, that obstructs the conditional dependence. It cuts it off. That allows us to simplify things. So now we no longer have that yi dependence. We get the simpler result here. And now what I can do is combine this model here for the first I-1 observations with the Zi state with our marginal model for the Zi state. So that's just refactoring those terms here in that third line. And that allows me to build this joint model for Zi and the first I-1 observations, which you might recall are those component probabilities, those derived component probabilities for the last state. this is the observational model. And if we sum over this, that's that form of that static mixture model. So another way of thinking about, why are we looking at this term in particular? Like, what's with this term here? This is the term we sum over to get the static mixture model-like form. In other words, this is the summand of a static mixture model, where we have the appropriate observational model, yi given zi, and now we have this, what we've kind of derived is what the form of those conditional probabilities look like. So we still have to do a little bit of work. Those component probabilities can also be written as a term that depends on zi minus 1 if we bring the Stroit model here, and then we sum over the zi minus 1, right? So we're doing the trick of kind of lifting it. We're adding a zi dependence and then summing over that zi dependence to get the same model. But this is going to allow us to derive this recursion. So the first term, where we have these kind of component probabilities that explicitly depend on the I-1 state, can be broken down, and again relying on the conditional dependencies, where knowing zi limits the interaction between some of these variables, blocks the coupling between those variables. And so if we go through the calculation, kind of combining terms, we get a form like this, where we have this transition probability. So in the last equation here, there's the transition probability, and then the zi minus 1, y1 to to I minus 1. Sorry, y1 to yi minus 1. That is that summand from the previous state. And now we're seeing the recursion coming in, right? If I want to calculate this summand of a static mixture model that I could sum over to get my full marginal model, I can derive that by taking the same summand from the previous state, multiplying it by transition probabilities, summing over the previous state, and then combining it with the observational model for that new state. And while I have this recursion, I just need to initialize it at the first state, and I can just apply this over and over again, and that'll allow me to sequentially marginalize every one of these hidden states, and one of these unobserved assignment variables. So the implementation of this recursive calculation is known as the forward algorithm, because we're moving forward along the sequence of hidden states. To make the math look a little bit cleaner here, I'm going to appeal to a kind of a linear algebraic or a vector notation. So we can think about the probability of the initial states. I'll think of those elements of a vector row. The observational model densities for each component model at the ice state. We can think of this as components of a matrix. And then finally, we have the transition probabilities for each possible initial state and second state or neighboring state. And these can vary by state as well. So we can think of this as a matrix at every state. We can think of this as a three-dimensional array, if that's more helpful. But I think the kind of array of matrices is kind of the most natural. Then these intermediate terms, the joint model for zi given the observations up to that point, I'll refer to that as alpha ik. So really kind of the evaluation of this at a particular state, and then a particular set of observations y. So we're evaluating this on real data at this point. We can think of this as again kind of elements of a vector at the ice state. And then with all of these definitions, if we go back to our original equation, well, the term we're calculating is this alpha I, k. And then all of the terms in that calculation, well, the recursive part of it, that's another alpha. And these other two terms, well, we get the transition matrix elements gamma. And then the observational model is just these omega elements. And if we look at this a little bit, this is a matrix equation, right? You can write it like this in terms of a Hadamard or element-wise product, where we take the previous alpha I minus 1 vector, multiply it by the transpose of the transition matrix, and then do an element-wise product with the observational model evaluations at that point. We can also, if you don't like Hadamard products, you can do this with just matrix vector products by taking this omega and turning it into a diagonal matrix. The danger here is that you don't want to turn the vector into a dense matrix and then do a dense matrix vector multiplication. That's going to choose a lot of unnecessary computation. So kind of the right way of implementing this is through a Hadamard product or an element-wise product. But if you prefer thinking just in terms of matrix vector products, you can also do that as well. So now our algorithm becomes extraordinarily straightforward to implement. You start with the component probabilities for the first state, which we need to model. They can't be derived from anything. Then we can derive all of the component probabilities for every state that follows using this recursive calculation. And at the end, we get a model for all the observations in Zi, and we just have to sum over those Zi's, which you can think about as summing over the elements of alpha I, which can be written in this matrix form. And again, this is known as the Ford algorithm. So how expensive is this? Well, at each step, at each iteration, we're going to need a matrix vector product. So that's going to dominate each of these recursive updates. And that's going to be k-squared operations. So the more component states we have, or the more components we have, the higher dimension of each state, the more expensive these intermediate updates become. And then we need to do that I times, where I is the number of these hidden states. So overall, our kind of computational scaling is I times k squared. If I and k, unless they're really small, this is drastically smaller, this overall cost, than the potential exponential scaling that we could get for an arbitrary coupling of these assignment variables. So this isn't necessarily cheap, but it's much less expensive than what the general case would be. And this is what takes the kind of intractable exponential cost and corrals it into something that we can potentially implement in practice. And to be clear, right, if there's a lot of these component values, if k is really large, or we have a lot of these hidden states, if I gets really, really big, implementing the Ford algorithm can still be very expensive. And it's not really parallelizable because it's recursive by construction. And so the overall cost of a hidden Markov model can be prohibitive in practice. Right? This can still be too expensive. It's just as kind of cheap as possible for these non-trivial couplings between the latent states, between these hidden states. So at this point, I do want to take a second to acknowledge that the notation and terminology conventions that I've used here are not universal. So there's two big places where you'll see differences if you look at other references, or you might see differences. Again, this is very heterogeneous across different references. So one is the inclusion of an observation for the first state. So you'll notice that I started with Z1, and there was a Y1. So the first state had an observation to it. A lot of references, Bishop, for example, assumes there's an initial state, Z0, that does not have an observation on it. And so you can always, this is always kind of possible to consider. If you have, wherever your first observation is, you just assume there's a state before that, right? And that's your Z0 that you include. The reason why this convention can be awkward in practice is you have a different number of observations and hidden states. So, for example, if you think about this observational so different number of observations and hidden states, and that just makes the indexing kind of awkward. So, for example, on a computer, there's like in R or in Stan, there's no zero indexing. So in order to index the latent states, you'd have to have a vector of length I plus 1. And then your observations would have a vector of length I. But the last element we indexed with I and I plus 1, not the same index as we have here, where they're both I's. So the advantage of the convention I've presented here is that it kind of makes the indexing a lot more straightforward. It's just easy to address the neighboring or the related observations and latent states. And then if you ever wanted to recover a model where the first state isn't observed, you can just take the elements of the observational model outputs at the first state and replace them with ones. And this is one place where having heterogeneous observational models from state to state can be very handy. So if there's ever a circumstance where there's missing data or you want to kind of turn off observations at a hidden state, you can just replace the model outputs by 1, and it's equivalent to kind of skipping over the observation at that point. And then the other potential difference is in the transition matrix. So the convention I've used is common in a lot of statistical references, but it's kind of awkward because we have to take the transpose if we're multiplying it by the alphas, right? So if you're just thinking about like the simplest calculation possible, you'd really want to define gamma in the opposite way, so we wouldn't have to take the transpose. We could just do gamma times alpha, and that would be kind of the simplest calculation possible. But in terms of interpretability, it's often helpful to think about the first state being the row and the second state being the column. And that's why it's used in a lot of statistical parlance. And so we just get the kind of transpose as a consequence of that. So Bishop takes the kind of more computationally driven perspective and defines it opposite to what we do here. And again, this is kind of heterogeneous. Some references do this, some don't. They're equivalent. It's just you want to be careful to make sure that whatever notation that you use, you're using it consistently everywhere. Any questions so far about the forward model? Okay, so the math isn't quite done yet. There's still some more things to do. The main problem at this point is that we've marginalized out the assignment variables at every state. We've gotten these coupled component probabilities everywhere. But in some cases, we might want to be interested in going back and looking at inferences for those latent states, right? So given the observations, we want to be able to say something about the consistent configurations of those latent states. So in theory, we can just apply Bayes' theorem. We can just partially evaluate the joint model, and that gives us a posterior, but this big, complicated joint model is not something we're going to be able to work with in practice. Instead, it's going to be much more useful if we can either generate samples from that joint model in an efficient way, or if we can look at marginals. We can look at just one hidden state at a time. Both of these can be done analytically with a little bit of work. So for example, if I just want to look at one of the latent states, I don't care about any of the others. I just want to know, given all the data that we've observed, what do we know about the ith latent state? Well, again, we can think of this as deriving this from an application of Bayes' theorem. We get the kind of opposite conditional on the right-hand side, and we get the prior for that ZI, or the marginal model for that ZI. And now we can start using the conditional structure of the hidden Markov model itself to simplify a lot of these terms. The first term, for example, ZI, the probability of all the observations given ZI, well, once we know ZI, right. The first I observations only depend on ZI. The dependence of the first I observations on ZI and the dependence of the last, subsequent observations on ZI are independent of each other, right? There's this kind of decoupling of the observations given ZI. And that's very handy for a lot of these calculations. So we can break up the model for the observations into these two models for the subsequent and preceding observations. Or the opposite, is it the other way around? The preceding and then the subsequent observations. And then recombine terms. And in particular, if we take the model for the first eye observations given the ice state, and then combine that with this model of P of Zi given theta, which we already had from Bayes' theorem, well, that combined is the joint model for the ice state and the first eye observations, right? We just computed that using the Ford algorithm. So we know how to compute that for every eye. All that's remaining is this term, the second term here, the last term there in blue, P of I plus 1 to I, P of y, I plus 1 to I, given Zi. Now, what's interesting is that this term can also be computed recursively, but that recursion goes the opposite way. So let's take this term we want to calculate here. We'll call it Bi Zi. Now, to calculate this thing, we're going to introduce the I plus first latent state. So we're going to do that same trick that we did before. We kind of lift this up to a larger model, introducing a new state that we marginalize out to recover the initial model. The reason we do that is that once we... we can then break this down into the observations given both the latent states, and then the model for Zi plus 1 given Zi. We know the model of Zi plus 1 given Zi. That's the transition probabilities. And then this model for the following observations given Zi and Zi plus 1, well, once I know Zi plus 1, that completely determines those preceding observations, right? The knowledge of Zi plus 1 obstructs any coupling or influence of Zi. So now I can drop the Zi dependence. And that gives me a model for... So we start here. I can drop the Zi dependence because now that I'm conditioning on Zi plus 1. Okay, there's a typo here. Right, so this should be Zi plus 1 here, not Zi. And then that should be Zi. Right? Ugh. Super compelling content as I just think really silently. That should be Zi plus 1. That's with the transition matrix element. And then you're going to peel off I plus 1, Zi plus 1. Right, so this dependency here is right. But this should be an I plus 1 then. The middle term of the bottom. So that the bottom equation there, first term has the right Zi, has the right I plus 1, but the second term should depend on Zi plus 1. Right. Okay. Yeah. So there's a kind of a few Zi's that need to be Zi plus 1s, but for I somehow corrected that here, where instead of being Bi plus 1 Zi, it's Bi plus 1 Zi plus 1. So that should be Zi plus 1 there, and then that fixes everything. So again, I need to fix it here, but the fact that this is Zi plus 1 is correct, and that's correct. So the final equation is right. So I'll fix that. Um, thanks for your patience. But the takeaway here is that we get another kind of linear algebraic looking equation. Once we make the substitution for omega and gamma, and we've already defined this intermediate term as a beta, we get this equation for beta I, not in terms of beta I minus 1, but in terms of beta I plus 1. So instead what we have is a backwards recursive relationship, where instead of trying to start at the 0th state and kind of sequentially move forwards along the states, we start at the last state and sequentially move backwards. And so unsurprisingly, we might refer to this as a backwards algorithm. The only tricky thing here is how we initialize it, so we have to be careful about, what should beta I be. And by just kind of explicitly calculating what this term is at the final state, we can see we get the right result only if we initialize at 1. So instead of initializing at these modeled initial probabilities as we do in the Ford algorithm, we always just initialize to 1s, and then we propagate that backwards. So putting all together, what we have is this combined algorithm that lets us calculate all the terms we need to compute the marginal posterior for the ith state, the ith assignment variable, given all of the observations. So we run the Ford algorithm from the first state all the way to the final state. We then run this backwards algorithm from the final state up to the state that we care about. And then we have these alphas and these betas that we can multiply together and then normalize, and that gives us these posterior probabilities. Unsurprisingly, this is known as the forward-backward algorithm, because we go forward and then we move backwards to the state of interest. Or if we think about going forward and then backwards all the way, we can then compute the marginal state probabilities for any of the intermediate states. This is also sometimes referred to as a filtering and smoothing operation. So filtering is the forward step, and then the smoothing is the backward step, where you can think about the filtering as kind of looking at the consequences of the first I observations. And as we add a new observation, how does that update our knowledge about the previous states? But if we want to know something about one of the latent states, given not just the observations to that point, but all the future observations, then we need this backwards recursion. And we can think of this as a smoothing operation, where we're kind of updating the inferences from the first few set of observations based on all the previous constraints that are happening, right? So we're kind of it's not really updating it anymore in the sense that it's kind of not we're kind of sequentially updating it based on y of I plus 1 and y of I plus 2. We're taking all of those constraints and imposing them all at once. And the nice thing about the forward-backward algorithm is that it's not really much more expensive, right? It's just another one of these k-squareds at every iteration. It's just increasing the cost by a factor of 2, which really isn't that expensive in the grand scheme of things. And it gives us all of this information. Moreover, we're only ever going to need this kind of information in the generated quantities block. So this backward sweep will be much less expensive because it's not using autodiff in a tool like Stan. Any questions on the backwards algorithm other than how I could make such egregious mathematical mistakes in that derivation? Okay. So, to be totally honest, the marginal state probabilities are, I don't know, dare I say they have marginal utility. The problem with looking at those marginal state probabilities is that they're marginal. Right? You're only looking at one state at a time. And one of the whole things about hidden Markov models is that we have this coupling between all of those latent states. We want to look at that joint behavior. So in practice, it's much more useful. It's often much more useful to work with the entire joint posterior for all of the latent states at once. To get anything useful out of that, however, we're going to need samples, right? If we want to be able to look at kind of arbitrary expectation values over all of those latent states, then we're going to want to look at samples. We can't sample from the joint posterior that we derived previously directly. It's just too big of a discrete space. But if we can break it down into conditional samples, if we can implement ancestral sampling, where we can look at, say, a sample for one state and then a sample of another state given that first state, sample for the third state given the first two states, and so on, that might be enough, or that would be enough to allow us to generate a joint sample of all of the states given the observations, and then use that to inform visualizations, expectation values, and the like. Anurag's mentioning in the chat that these kind of forward and backward algorithms look a lot like belief propagation, and they absolutely are. So another way of thinking about this from that more kind of computer science perspective is that the Markovian structure of a hidden Markov model allows belief propagation to be implemented analytically. And so it's one of the cases where you don't have loops, so there's no kind of loopy belief propagation or anything like that you need. Everything kind of converges in a very simple way. And so you can use belief propagation calculations to derive the forward and backward algorithms. And that's one thing Bishop mentions. So the Bishop's pattern recognition and machine learning, if you haven't seen it before, highly recommend it. It is a little computer science-y. And so while it's basically like, hey, look, here's all of these machine learning methods that are really just Bayesian inference, it doesn't really hammer that home, so you have to be aware of what's going on there. But once you're aware of that, I think Bishop does a really good job of kind of explaining the details, talking about implementations, connecting ideas, really kind of insightfully presenting intuition and the like, or a lot of different techniques. So great book, highly recommended, especially for hidden Markov models. Where he connects it to things like deseparability, belief propagation, and the like, and then kind of continues on to more general belief propagation algorithms where you don't have these nice analytic results, and you have to do more of approximate belief propagation. Okay. So what we want to do is be able to look at the joint state behavior. In particular, what if, for example, I wanted to look at trajectories of the hidden states. I wanted to look at, realistic paths through the component assignment variables. We can't do that with the marginal probabilities. We need joint behavior to do that. So what we're going to do is try to generate these samples one at a time. And this raises the question of what order do we want to do it in. For example, do we want to sample the steps going forwards, right? I want to generate the first, a value of the first state, and then a value of the second state given the first state, and so on and so on. That's definitely a possibility. The only problem with this is you'll note that we're trying to sample posterior states here, right? So I want to generate not just Z1 given Y1, I want to generate Z1 given all of the observations. And that requires information that's happening later on at those other states. So just intuitively, from kind of an information perspective, if I want to generate a posterior, it's going to depend on all of the states, and I need information from all of the states, even though I just want to generate a value for that first state. So going forwards intuitively really shouldn't get us the answer that we want. Going backwards, however, that's where things become more reasonable. Because if I've already ran, say, like a forward algorithm, gone forward along the hidden Markov model, I might be able to aggregate all the information that I need, collecting the constraints from all of these observations, so that when I'm at the last state, I can then generate a sample informed by all of the data. And then I can go to the second to last state and generate a sample informed by all of the data and that last state, and so on and so on, right? So just intuitively, recalling that we're looking at posterior samples, going backwards along the hidden Markov model makes a lot more sense. So this suggests a recursive calculation where we're trying to compute z of I, not given we're trying to compute a conditional probability, conditional posterior probability, not of zi given zi minus 1, rather zi minus 1 given zi. And so this is the last step we're going to need for the math, right? We need this conditional probability, which you can think about as being derived from Bayes' theorem, over just those two states. Those two states, remember, however, this kind of dependence on yi plus 1 and zi minus 1 and zi, there's going to be this kind of blocking, this obstruction of the dependencies. So we're able to simplify this a little bit. So first thing we'll do is we use Bayes' theorem to flip the conditioning here. So we go from the states given the observations to the observations given the states, and then a model for the states. Now I use this result where I can break up. Let's see, what am I doing? Nope, sorry. Before even getting to that, given that joint model for the two states, I can think of it in terms of transition probability, and then I just have an extra term here that I don't need. So I've duplicated that last line. The third and fourth lines are the same thing. At this point, we can take advantage of that blocking, that obstruction that we get from these latent states, so that the probability of all of the observations given zi plus 1 and zi, that really breaks down to the probability of the first I minus 1 observations given zi minus 1, the probability of the ith observation given zi, and the probability of all the future observations given zi. Right? So it's kind of a generalization of that obstruction that we used previously. We just are conditioning now on two states instead of one. And once we plug that in, things simplify quite a bit. So we kind of combine a bunch of common terms together. And one thing, to keep in mind is all of the terms we've already know how to calculate recursively. So in the end, we get something that looks like this. And you might notice that you have terms like this. That's an alpha. And you have a term like this. That's an omega. And you have a term like this. That's a beta that we know how to calculate. And a term like this, that's a transition probability. So we can write all of these terms in terms of gamma, beta, alpha, omega. And we can turn that into a matrix calculation. Oh, it's a little awkward because we're conditioning on, some of these vectors are we're getting single elements out of based on the sample that we previously generated. So putting this all together, once we've run the forward and backward algorithms, we have all the information that we need to generate conditional samples of the joint states. We run the forward algorithm forward. At the last state, we can generate zi given the observations using the alphas, right? The alphas are exactly that term of zi given the observations. Normalize them, and that gives us our final state. Then we can start running this recursive reverse conditional sampling, where we compute the conditional probabilities of zi minus 1 given zi and the observations, all the observations, normalize that into probabilities, sample from that, and then continue going on. And you'll notice here that we don't even do matrix vector multiplication anymore. This is just linear operations, and so this is basically trivial compared to the cost of the forward and backward algorithms. And there's actually a few things we can do with this. From a Bayesian perspective, we're going to be using this to generate samples. Posterior samples of the latent states given all of the observations. But if you wanted to, say, find a maximum a posteriori trajectory through those states, you might look at the most probable final state, you might look at the most probable penultimate state given the final state, the most probable zi minus 2 given the most probable zi minus 1, and so on. And they'll give you this notion of kind of a highest probability trajectory. That's what's called the Viterbi algorithm. So we're not going to use that here because we'd rather look at ensembles of trajectories rather than one maximum probability, maximum posterior trajectory. But if you've heard of HMMs before, or common filters and you heard of the Viterbi algorithm before, that's just basically doing maxime a posteriori on using this information. Okay, so that's most of the math done at this point. Any questions while I take a big drink of cold water? Okay. So again, you can kind of see how I've even taken some shortcuts in that derivation. There were definitely some properties that I did not derive myself because they're a giant pain. I just appealed to Bishop, which appeals to Jordan et al. And it's mostly just trying to kind of build some intuition about, you know, why we have to go forwards and backwards, why we have to go forward and then backwards, why samples have to be generated recursively from the final state to the initial state, and so on and so on. But if all you really care about is the final algorithm, if you kind of just take, you know, trust that we're doing the right thing here, you can just jump to the end of these sections and get these calculations, right? Just say, like, look, I don't know what these alphas are, I don't know what these betas are, they do something interesting, and I'm going to just take them as is, and I trust that whatever, you know, when I combine them together at the end, I get these terms that I want. That's totally fine. In fact, when we cut to implementations and standoffs, we'll see a little bit later, there are functions that do all this for you. So you don't have to worry about this for most cases. So definitely don't get caught up on the math. It's nasty. It's going to take time. If it's something that you want to work through, absolutely go for it. It's just going to be a lot harder than most of the other derivations and calculations and all of my writing so far. This is definitely on that edge of abstraction where it's so close to just wanting to, like, hide the calculations, but it's so kind of needed to motivate why we can do it in this case and why we can't do it in others. All of that said, these algorithms as is are still not quite enough for practical purposes. The problem is that if you look at the recursive calculations that we have, so let's say we go to, let's go here, right? Notice that, like, in the forward calculation for the alphas, we're not adding terms together, we're multiplying them, right? We're multiplying an alpha times a gamma, and then that alpha gets multiplied by a gamma and an omega. And all of the multiplication of these transition probabilities and observational model densities, that can very quickly underflow. You can actually do the calculation for you, or you can do the calculation yourself to explore it. After about 10 states, this underflows. It's wild how fast it happens. So we can't just implement this as is on a computer because floating point arithmetic isn't sufficient for it. Yeah, JD. Yeah, it's. I think I want to go back and be a little more explicit. Like, these are brutal calculations. I think I'm gonna have to just use that term. They are brutal calculations, and they're hard. And it's okay to skip them. This is a case where we don't need to understand the results if you just are comfortable using the method. As we'll see a little bit later, the results give it basically everything that we need. There's really not much that we need to generalize that's going to be all that useful in practice. So, like, you know, a lot of reasons you need to know the derivation is so you can modify it later on. And I think it's true of a lot of methodologies. But here, not so much. Especially once you understand mixture observational models and the marginal form of mixture observational models, a lot of this can kind of be intuited, and if you just take for granted the calculations. But because so many people don't believe this is possible, right, there are entire fields that just refuse to do hidden Markov models instead because they don't think it's real. There has to be some kind of argument for it, right? And I don't know. So it's I don't know. Maybe I'm doing too much with this chapter, and maybe it is better to put into an appendix. But that all has to have to kind of come from, you know, we'll iterate, right? You can always change this and improve it. So if you find this to be too distracting, let me know, right? And if there's enough votes that it's like, yeah, this is cool, but it's too distracting. I'd rather just get to the results. I could easily see this chapter, all these calculations being moved to the appendix, and my just saying, here's the term we want to calculate. We can kind of see why it would be useful from a kind of a static mixture model analogy. Go to the appendix for the derivation, which is long and nasty, which I do in a lot of other chapters. And so maybe that's going to be the best way of putting this together. Let me know. It's not a problem. This is the kind of feedback that's really helpful for me. So don't hesitate to share. All right. So our problem in implementing these algorithms, if we're multiplying these terms, multiplication's not great. Repeated multiplication is not super stable on a computer. So there's a few ways around this. One way around it is to work on the log scale. So instead of working with the alphas and omegas and gammas, what if we work with log omegas and log gammas and so on? So if we try to take a log of both sides of the forward equation, for example, you can see that it kind of reduces to a log sum x calculation. So we're going to get kind of every column, the matrix vector product of the transition matrix times the alpha can be broken down into a bunch of vector-vector products, and each of those vector-vector products can be thought about as a term in this log sum x. So we get the log transition probabilities, we get the log alphas, we get the log omegas. So we have a recursion for the log alphas. It's just a little bit more awkward. In theory, we could do a log sum x on the backwards pass as well. However, in the backwards pass, you'll note that we're always kind of renormalizing to get things. So we don't... Oh, sorry. I'm wrong. Let me hold off on that. If we want to avoid underflow in the betas, we also need to do log sum x there as well. So you'll see this log sum x approach in a lot of tutorials for HMMs, especially HMMs in Stan. But all of these log sum x require a lot of exponential calculations. We're logging things, we're exponentiating things. That's really, really expensive, especially if we're doing it over and over and over again. So it's stable, but it's expensive, and there's a faster way of doing this. So the trick, instead of trying to log sum x, is to dynamically rescale these intermediate terms. Instead of just computing all of the alphas, we compute the alphas, divide, compute the alphas, divide, compute the alphas, divide. So the value of alpha at any given I is a more moderate value. We kind of prevent that underflow from happening. So, for example, I might do something like this. I'm going to define AI as the output of this nominal calculation. And then I'm going to calculate the largest value, the largest element of that output. And I'm going to define the next alpha not to be the AI, but AI divided by that maximum. So that at every iteration, the value of these AI prime elements are all kind of around 1. So things can't get too big, they can't get too small. Now, if we compare these alpha primes to the original alphas from the forward algorithm, they're all related to each other by these rescalings that we did. In fact, it's just a product of all these terms, right? And you can start to see like where this underflow is coming from. If the alpha I primes are nice and numerically stable, but this term here, where all of these nus, all of these coefficients that we're normalizing by, multiply those all together, this is really prone to underflowing, which is why the left-hand side is prone to underflowing, right? All we've done here is kind of isolated the numerically unstable or poorly behaved part of this calculation. But because we've isolated it now, we can just deal with this product more stably, right? Let's compute the alpha primes as we did, using this recursive calculation as is. No need to introduce log sum x up here. When it comes down to computing this product, well, that's straightforward. That's just taking the log of those norms, summing them up, and then taking an exponential, right? But now it's 1 exponential for the entire thing instead of all these exponentials at every iteration. So overall, this becomes much, much less expensive than trying to use the log sum exp. I should say much expensive. It's I think, if I remember correctly, it's like a factor of between 2 and 5 faster. And it all depends on, how many components you have at each state, how many states you have. So, there's some kind of scaling there. But overall, you don't really lose any stability using this approach. And it tends to be a little bit faster, even in the worst case. So it's just kind of, universally better than using log sum exp. And then what's even better than this is, while we have to keep track of these normalizations when we do the forward algorithm, when we do the backwards algorithm, we're going to be renormalizing all those probabilities anyways. So the scale factors, these normalizations that we introduce, would cancel out. So we don't even have to do that. So it's this really nice, clean thing that when we're doing the forward algorithm, we have to rescale, save the rescaling so we can correct for them. When we do anything else, the forward backward, when we do the sampling, we still have to rescale the betas, but we don't have to keep those rescalings around. So now we have forward-backward algorithms, things that we can derive from the forward-backward algorithms, and we know how to do this all very stably on a computer. There are still a few kind of bells and whistles that we want to consider to really take advantage of HMM as a whole. So one thing that we're going to have to worry about is modeling the initial state, right? The forward algorithm gets initialized at the component probabilities of the initial state that we have to specify. Now, there's a few ways of doing this. In most cases, we just want to think about this initial, what do we know with that first state? What kind of values can it take? Or if we don't really know anything, do we just use a uniform Dirichlet prior or something like that? Uniform over the simplex of initial probabilities. But in some cases, it can be more helpful to think about an HMM as being in a kind of equilibrium. So the idea here is to recognize that if we organize our transition probabilities into a matrix, then these matrices will have eigenvectors, right? There will be certain inputs to matrix vector products that are preserved by that multiplication. And that will have a very nice physical interpretation. So in particular, the transition matrix, the elements are between 0 and 1, right? They're all probabilities. And the rows, each row of a transition matrix sums to 1. This is known as a row stochastic matrix or a right stochastic matrix. And what's interesting about these stochastic matrices, these particular right stochastic matrices, is that they always have an eigenvector whose eigenvalue is 1. And all of the other eigenvectors will have eigenvalues with absolute value with magnitude less than 1. Right? So it's always going to be kind of like the highest eigenvector, this kind of dominant eigenvector who has the largest eigenvalue, and the eigenvalue is 1. So what's special about an eigenvector with an eigenvalue of 1? Well, if we multiply a transition matrix by that eigenvector, or in this case, it's a left eigenvector, so we multiply it by the transpose, which is the operation we're going to be doing over and over again, right? We get 1 out, which means we just get the eigenvector back, right? So this top eigenvector, this top left eigenvector, the transition matrix is basically an identity to it, right? It's preserved. It doesn't really get modified. Every other eigenvector, however, will have a smaller eigenvalue. And so if we multiply any other eigenvector by this transition matrix over and over again, those smaller than 1 eigenvalues start multiplying and multiplying, getting smaller and smaller and smaller, and just like we saw before, go to 0. Although in this case it's exact and not just a consequence of floating point arithmetic. So if I take any vector, any set of probabilities, and I decompose it into the kind of projection onto this left eigenvector, this dominant eigenvector, and then all of these subleading eigenvectors, all of those subleading components go to 0, and the only thing that persists is this dominant eigenvector. And what this implies is that there is one set of probabilities that will persist forever. If we start the system in that state, the system will stay with those component probabilities everywhere. And if we don't start it in that state, it will eventually converge to those component probabilities. So this is known as an equilibrium system, right? That there is this stationary behavior for these component probabilities. And either we initialize there, or if we initialize somewhere else, we'll eventually get there if we wait long enough. So if we want to model a system in equilibrium, then we don't have to model the initial probabilities ourselves. We can derive them as the appropriate eigenvector from the transition matrix itself. Now, unfortunately, this is a little bit trickier to implement in practice than it is to just state, right? From a purely mathematical perspective, we have a transition matrix. We derive the left eigenvectors. We find the left eigenvector with an eigenvalue of 1, and we just take that as our initial probabilities. In practice, however, that's not always going to be straightforward. Most eigensolvers that you get aren't going to rank the eigenvectors by their eigenvalues, and if they do, it's going to be a numerical ranking, right? You could have an eigenvector that's really close to 1, but not exactly 1. And you might not be able to tell the difference of those two with floating point arithmetic. So you run into this kind of awkward situation where you have to kind of write code that's going to calculate eigenvectors and eigenvalues, and then do a check to see if one of those eigenvalues is not necessarily exactly 1, but close enough to 1 for floating point. And those eigenvalues in general are going to be complex, except for that top eigenvalue. So now you have to do magnitudes and floating point and complex numbers, and it's all just a giant mess. So it can be done, but it's not elegant by any means. Now, in theory, you might be working with a tool that provides specific eigensolvers for stochastic matrices. That would make this a lot easier. Stan, however, does not. Stan only has these kind of general eigendecompositions that introduce complex matrices and complex eigenvalues, and those are kind of awkward to work with. There's also the eigensolver for symmetric matrices, but stochastic matrices are not symmetric in general. So yeah, kind of one of these kind of awkward things to implement in theory, although it can be done if you really care about it. I would say in most cases, you're probably just going to do like a very diffuse prior on those sort of probabilities, unless you know something very strong about the initial kind of how the system was started. And the other thing to recognize is that if you don't have homogeneous transition matrices, if it's not the same transition matrix at every state, this notion of equilibrium doesn't really matter anymore. Yes, there's a separate eigenvector that's preserved at every state, but it's not the same eigenvector preserved at every state. So you don't get this kind of long-run behavior that kind of projects out everything but that one eigenvector. Instead, with a heterogeneous hidden Markov model, you're kind of projecting out different vectors every time, and just nothing kind of stabilizes that, or you don't converge to anything. All right, so that's the initial state. This one's fun. So there's a lot of cases where there's not necessarily one latent state of interest, but rather multiple latent states of interest, right? Like the behavior of the observational model really is best thought about as depending on these kind of two variables at the same time, instead of one long variable. This comes up a lot in a lot of scientific applications, and we'll see an example of it in the demonstrations. So this raises a question of how do we implement this in practice? Well, in theory, regardless of whether these kind of latent sequences are kind of coupled together as they are in this top figure, or they're kind of independent latent sequences as they are in the bottom figure here, we could try to derive general forward and backward algorithms. It is possible. So we can have these kind of forward backward algorithms where we're kind of updating multiple sequences at the same time and implement that. But especially if we're not comfortable with those derivations, or we're going to use functions that implement them for us, that's not going to be the best approach. One way to leverage existing tools is to not modify the forward and backward algorithms, but to take these composite latent states and combine them together into a single latent state. And fortunately, there's a systematic way of doing this from linear algebra. So we're going even deeper in linear algebra here, right? We've had to do all of the calculations for the forward and backward algorithm. We've had to do the linear algebra for the stochastic matrices. Now we're going to do tensor products of vectors. So if I think about every latent state as a vector, I can combine them together using what's called a Kronecker product or a direct product or a tensor product. And what that does is it combines all of those values into basically an ordered pair or an n-tuple. So if I'm combining m vectors together, I'm going to get a single state that's an ordered m-tuple where I can pick one value from each of those vectors. So as an example to this, if I have these two latent states, z1 and z2, the first one has 3 possible states, the second one has 2 possible states. Then the tensor product of the two is built up of the 6 possible ordered pairs that I can get from those. Right? So I can have 1, 2, or 3 in the first slot, and I can have 1 or 2 in the second slot. And that fills out these values. There is, note, a convention here on how you order these. This is going to be important in a second. So this is kind of the standard convention where you fix the first element, and then you allow the next elements to vary, and so on and so on. So, like, if I'm doing m of these, I fix the first m minus 1, and then I scan through all the possible values for the last component, and then I fix the first m minus 2 and allow the second one to go, and so on and so on. And that just gives us like a systematic ordering of these tensor states. So that, in particular, I can take the tensor states and then I can map them into the integers, but that requires an ordering. So this kind of mapping can be permuted. This is just one particular systematic convention for doing this. Now we want to be careful here. If we're going to combine a lot of states together, the number of tensor states gets really big really fast. And that can first be ungainly to deal with, but can also make the HMM too expensive to run. So just be careful that, just like so many other tools that we're talking about here, we're really on this knife edge of practicality. If we try to push these models too hard, we'll fall on the other side. It won't be all that useful in practice. And the kind of multiplicative scaling of tensor products with the number of dimensions in the component variables, a number of possible elements, can explode really fast, and that will then start amplifying the cost of the HMM, because it's going to scale quadratically with this product here. So the only other thing that we need to do at this point is to construct a transition matrix for these tensor states. And there's a few ways of thinking about this. We can just think about it as this kind of big monolithic tensor matrix over this larger tensor state. We can think about the transition probabilities in terms of the individual components. So here's kind of like the monolithic picture, right? Where we're looking at, Zi and Zi minus 1 are taking values not on the left-hand side, but on the right-hand side. If we want to think about it in terms of m-tuples, then we can just have the individual components of those m-tuples and think about the individual components that we're transitioning between. This is particularly handy here when the states that we're composing together, that we're tensoring together, are really interpretable, and we really want to maintain that interpretability. Oftentimes it's easiest to keep working with those ordered m-tuples. There's a special case here where things simplify. When two states are evolving independently of each other, So the case here on the bottom figure, where there is, the behavior of Z2I only depends on Z21, not Z11. In that case, we can actually derive the transition matrix for the entire tensor state as a tensor product of individual tensor matrices for each of those independent sequences. The only thing that we have to be careful about here is the ordering. So just like before, the kind of ordering and how we construct that tensor product matters. If we're not consistent about it, then the calculations we get won't make any sense. So for the example here, we consider two binary latent states. This is giving us 4 ordered pairs in the tensor product. We can encode those as 1, 2, 3, 4 by using this very specific ordering. And then we can construct transition matrices for those two states. So they'll be 2 by 2 matrices. And then we can combine them together into a 4 by 4 matrix using this tensor product structure. So we basically kind of first expand it into the elements of the first transition matrix multiplied by the entire second transition matrix, and then we expand those. So this kind of term here expands into the first top left block of the 4 by 4 matrix. So this is again a kind of a systematic way that you can do this. And the kind of only subtlety here is in the ordering. So it's not commutative. So you can't just like change the order up of things or also get these permutations of these matrices. It's going to take a little bit of care to make sure that things are consistent. But this only works if you have the independent latent states. If you have coupled latent states or these latent sequences, we're going to have to work through all of these transition probabilities for all of those components, which can be a lot, but sometimes you have to do it. So this is definitely kind of an advanced feature of HMMs, but as we'll see in the demonstrations, it can be really handy in practice. So when it's like you don't need it for most cases, but when you need it, it's really helpful to have it. And then the last thing I want to mention here is missing data. So formally, dealing with missing observations is pretty straightforward in a hidden Markov model. So if we can try to handle this formally. Take the joint model, right, and just marginalize out the ith observation. So we have the model that we've already built, and we're trying to marginalize out over yi. We expand everything, we isolate the terms, kind of focus the integral where it matters, which is just on this term here. Right. Remember, the observations aren't coupled to each other; they're only coupled to the corresponding latent state. So when I can get to that one observation, I'm just getting rid of that one observational model. Everything else stays the same. All of the coupling of the latent states is the same. All of the observational models for the other latent states stays the same. So what's nice about this is that if I want to get rid of an observation at one of the states, I can explicitly remove it, or I can just set those observation model outputs to 1, or correspondingly the log observation model outputs to 0. What's really, really nice about this is that we don't have to change the forward-backward algorithms. Right? We don't have to have a kind of a conditional forward-backward algorithm where if there's no observations, we use one calculation, and if there is an observation or there are observations, we can use another one. We can use the standard forward-backward algorithms. We just replace omega with 1, or log omega with 0, whenever it's appropriate. The only reason why this can be suboptimal is if we have repeated observations that are missing. Right? So if there's a whole sequence of, say, 10, 20 states with no observations, there's something kind of inefficient about keeping track of all of those latent states if we don't need them. Now, sometimes you want to infer the latent states where there are these gaps of observations. If we don't care about those latent states, we just want to, get to the observed latent states and see what's happening there, then another thing that we can do is just collapse the entire HMM. So for example, here I have these two latent states that are unobserved. I could model this by just replacing the omegas at I plus 2 and I plus 3 with 1s and run forward backward algorithm totally fine. Another way of doing it, however, is to get rid of those states entirely. Just jump from zi minus 1 to zi plus 4 and then reindex everything. And then all I have to do is replace the transition matrix from zi plus 1 to zi plus 4 with the product of those intermediate transition matrices, right? So instead of jumping from I plus 1 to I plus 2, and then I plus 2 to I plus 3, and I plus 3 to I plus 4, I can just multiply those transition probabilities together and then run the standard forward backward algorithm using this smaller set of states. So this can be really, really handy when there are these long gaps and you don't want to have to deal with propagating things through those gaps. It's not in general always going to be a useful solution, however. So if you do want to make inferences on those latent states that are unobserved, are not paired with observations, this isn't going to work because you're marginalizing out those latent states. That's not helpful. This is also going to be problematic because let's say, for example, that all of your transition matrices were homogeneous. When you collapse out some of these states, at least one of those transition matrices becomes different from the others because it's a product, right? It's a power of that base transition probability matrix. And so now you have to go from, say, a homogeneous HMM implementation to a heterogeneous one, which may not be directly available. So, for example, in Stan, there isn't a heterogeneous HMM functionality, so you have to write that yourself. But it can be handy. Again, these are kind of more advanced ideas. You don't need them for basic HMMs. You can get away without them by just, for example, setting the observational outputs to 1 when necessary. But every now and then, you'll see an application where this is really handy. Now, those implementations for missing observations assume that the observations are effectively missing at random. When we have circumstances where observations can be missing due to other behaviors, then we have to be a little more careful. Right? So just like in general, when you're dealing with missing data, if it's missing at random, it's usually pretty straightforward. But if it's missing based on some other behavior that you're modeling and you ignore that coupling, you get selection bias and all those terrible inferential behaviors. So one way of trying to accommodate more complicated mechanisms for missing data is to introduce a parallel latent sequence that's observed that indicates whether or not a latent state has any observations or not. And what this allows us to do is model the couplings between these observed latent states and the unobserved latent states, these known latent states, whether or not there's an observation, and then these, other latent states that are controlling the behavior, the dynamics of the system. And so by, introducing non-trivial structure here, you can have all kinds of kind of intricate couplings, but models for why data goes missing based on the underlying dynamics of the system. So, if things are, moving too quickly or they move to an extreme, then you might have more missing data and the like. And this is where you can start accommodating more complicated behaviors. And again, it's this kind of basic structure of an HMM, but by leveraging, additional latent sequences, and then, for example, implementing that using the techniques we talked about up here, right? We can start adding layering all of the structure into it while using the same forward-backward algorithms. So we put a lot of work into understanding the forward-backward algorithms and their consequences, so that we have this really generic tool, and now we can start applying it in all these different cases. And there's the immediate cases, but there's also these not quite immediate cases where it's not necessarily obvious that you can use a forward backward algorithm. In these cases, you have to introduce an initial latent sequence and then combine that, tensor that with your initial latent sequence. You might have to combine transition matrices together, and so on, right? So these advanced techniques are all about kind of like really recognizing how far we can take these ideas so that when we come to an application that needs this complexity, we're ready for it and we can take advantage of it. Okay, so this section is relatively short, and it's really just a cry, a plea to do not use exchangeable mixture models with HMOs. There are a lot of tools out there in various programming languages that basically implement hidden Markov models where the component observational models at each state are a bunch of normals. And there is nothing separating those models from each other, right? So it's completely exchangeable. All you're doing in this case is taking the degeneracies of that static mixture model and amplifying them every time you add a new latent state. It's so bad. It's so horrible. So Anurag's asking what an exchangeable mixture model is. So this is discussed in the mixture modeling chapter, which I highly recommend you take a look at if you haven't seen it yet. There's the chapter, and then on the Patreon, if you go back, you can search mixture model chapter, or you can just go back, scroll back a few months. Or I guess at this point, it's more than a few months. It was end of last year, I think, I did this chapter. There's another video that reviews this chapter. It talks about exchangeable mixture models and why they're so bad. So I definitely recommend checking those out. But basically, when you have a mixture observational model, right, you have these component observational models. If those component observational models are the same, say they're all normals, then you run into these problems where the observational models can flip, and it doesn't change the output, right? So like say you want to model some kind of bimodal behavior, and so you have these two normals that you want to combine. Well, I could take one of those and make it the lower one, and one of them make it the larger one, but I could also flip it and have the other one be the lower one and the other one be the higher one. I get equivalent fits that way. So when I look to quantify my posterior inferences, I'll get this multimodal posterior because I can switch those two assignments without changing the output of the model. And that's just horrendous to deal with computationally. And it gets worse as you go from 2 components to 3 components to 4 components. That's the thing, right? It's on this label switching, the likelihood output is exactly the same, because the component observational models are exactly the same. So if I swap a normal for a normal, they just reconfigure themselves to match those 2 behaviors. So I have these if I have 2 components and I have these 2 modes I want to match in the data, there's 2 different ways I can do that. If I have 3 component models and 3 modes I want to match in the data, then there are 3 factorial, 6 ways of matching all those together. So you get 6 peaks in your likelihood function that all have exactly the same values. They're all equally good fits to the observed data. So this is known as the label switching problem, multimodal degeneracy. There's a lot of descriptions of it in various literature. Different fields will use different terms. So you have to distinguish those observational models in some way. You have to enforce that some of those component models are responsible for certain distinct behaviors and others are responsible for other distinct behaviors, right? That's the only way you get nice likelihood functions and tractable posterior inferences. And so things like orderings can help, and there's other tricks. The prior can help separate out those variables, those component observational models a little bit. But even with those, with a kind of some kind of constraint that technically keeps them distinct, you can get approximate degeneracies where maybe you get these peaks in the likelihood function. Maybe they're not exactly as high as this one ideal mode. but they're so close that you're not, for all intents and purposes, they're equivalent. And with something like Hamiltonian Monte Carlo, or really any Markov chain Monte Carlo technique, you're not going to find all those modes, let alone be able to quantify the relative weight of each of those modes. So it's a horrendous problem, and it's all due to building a bad model in the first place. So again, I highly recommend checking out the mixture model chapter and then the video review of the hidden Markov of the mixture modeling chapter, where I rant for quite a long time about these exchangeable mixture models. There's a whole exercise that shows how bad they are and tries to kind of like explore it and make it happen, and you just can't make it happen. Yeah, there's 6 equally good maxima. In fact, here, I'll show you a real quick. So again, I recommend checking out the video because I go into great detail about it, but just really quickly. So here's an example. So this is there's kind of, you can kind of see 2 peaks in the data, and I have these 2 component normals. In the first figure down here in B, one of the components grabs that first peak in the data, the other component grabs the second peak. In C, they flip, but because they're the same models, they can reconfigure themselves to reproduce exactly the same thing. So in A, if you look at the likelihood function for this model, say in terms of mu1 and mu2, the location of those component normals, it's exactly the same. In fact, it's a reflection symmetry across this plane. And that's what the label switching always has, these like very distinct reflection symmetries to them. So it's exactly the same. It's because the model's too redundant. There's 2 different ways the model can get exactly the same behavior matched to the data. And so you get those 2 modes in your likelihood function. And it gets worse as you add more and more components. So check out in particular this exercise here, where I try to do a 3-component model, and it just gets worse and worse and worse, and it gets bad and bad. And and then if you have questions about that, you can throw the questions up on the mixture modeling chapter post or the mixture modeling live stream review post, and I can help you there. Right, so if you take a bad mixture model and then repeat it, it just gets worse. What a hidden Markov model can do, the one place where HMMs can be a little bit helpful, is the rigidity of the latent states can sometimes help make poorly informed mixture models a little bit more informed. Right, so for example, if you have one set of observational models that in isolation, the data just really aren't strong enough to really inform what's going on there. And so you have a lot of degeneracy, or a lot of degeneracy in the component probabilities. When you add the coupling of the latent states, if the previous latent state is strongly informed by its data, and the following latent state is strongly informed by its data, and the transition matrix is strongly informed, right, that's going to strongly inform that intermediate latent state, even though there's not a lot of data there. So if things are kind of, if things are bad, then HMMs, like, it multiplies all of that badness. And it gets kind of exponential growth of horrible. But if everything is kind of sort of well-behaved, then when you multiply it together, you can actually get better results. So it's one of these things where if you're careful, you can get a lot of benefit out of this approach. If you're not careful, things can get arbitrarily bad. And there's a lot of HMM tools that don't let you specify your own models. They will just basically run a HMM with mixture normals. And I cannot tell you how terrible those results are. They're really, really bad. They lead to a lot of really fragile science. And those tools are very popular. So just be really careful with HMMs. A useful HMM requires useful component models. And turbulent component models that are responsible for distinct behaviors, that's where you get your real benefit. Okay, so 2 hours in, we finally get to the demonstrations. And these are by no means, exhaustive of everything that you'd ever encounter with an HMM. But, as always with these demonstrations, the hope is that they just cover the basics, right? They set you up so that you have a sense for how to use these tools and then how you might generalize them going forwards. So the first thing we're going to do is look at different implementations. So we're going to simulate some data from an HMM. So we know the number of components, everything is nice and well behaved. And this just code shows you how you can simulate sequentially, right? So that joint model, when there's no conditioning on data, is really easy to work with because you can just scan through it in the forward direction. So you can sample initial state, you can sample data from that initial state, and then you just continue on. You multiply, use the right row of the transition matrix to get the probabilities for the next state. So you get that kind of conditional dependence, and then you sample the next state, and you sample the next observation, right? And so on and so on and so on. So in data, you can see there's these kind of two clear distinct peaks. There's actually a kind of a third peak here in the middle, right? And that's one of those more subtle things that you don't always see from the data alone. That's where the model is really helpful to kind of identify that extra thing going on there. We can plot data marginally as if we were just going to do a single mixture model. We can also plot it by state, right? We can kind of look how it evolves across the states. This is referred to as a trajectory sometimes. We're looking at how the data changes, and you can kind of see there's these distinct behaviors. Sometimes the data is really high, sometimes the data is really small, sometimes it's kind of somewhere in the middle. So the first thing we'll do for the HMM is try this logsum-x implementation. I debated doing the naive forward-backward, but it just breaks so hard. I don't know how useful that is, right? It basically it underflows to 0 immediately, and you just get rejections everywhere. It's kind of a weird pathology. So it's kind of hard to miss. So I'm just going to jump to the ones that behave a little bit better. But if people think that might be useful, again, let me know. Right. So we have our priors for everything. I'm using uniform priors for all of the simplices here. We get our log transition probabilities. We get our log rows. We do our logsum-x calculation. And then at the very end, we do logsum-x of that last log alpha, right? So notice here, I don't need to save all the alphas. I just need that last alpha, and then I need to sum over the individual values. So there's a logsum-x there, and then there's a logsum-x in each one of the iterations. That's really where the cost is building. In the generated quantities block, I have to rerun the forward algorithm, and I need to save those alphas because I need them for each state, right? I need those for multiplying by the betas in the forward-backward algorithm to get the marginal state probabilities, and then I also need them for computing these conditional posterior probabilities. So once I've done the forward algorithm again, I can now do the reverse algorithm, the backward algorithm, and then along the way sample states. So I can sample the final state, and then I can compute initialized beta. I get the marginal probabilities for that last state, and then iteratively update everything. So we get the kind of new lambdas. I sample the state. I get the new the posterior predictive observation. I update the betas using logsum-x, and then I compute the latent state probs. So everything looks good computationally. Doesn't look like HMM Hamilton Monte Carlo is having any issues trying to quantify this posterior. We get a nice retrodictive fit, so no kind of indications of model inadequacy. And we can see the dynamics of the latent states. So here these are the posterior predictions for the observations in red, and then of course the observed data itself in black. And you can see that we're kind of matching those dynamics, right? Our predictions are changing in the same way that the observations are. So there's no indication of model inadequacy. Both of these are really helpful here, right? This check here is really helpful for getting a sense for whether or not your observational model components are sufficiently robust. And this check here is really, really helpful for making sure that your transitions are rigid enough or not too rigid. You can imagine, if you see your posterior predictions are kind of like trying to go up, but they're not going all the way, that's a good sign that maybe you're over-regularizing your transition probabilities. So we get our inferences for all of our individual parameters. These might not be immediately easy to interpret. So instead, what's helpful is looking at some of these kind of more direct inferences, right? These kind of consequential inferences derived from our parameter inferences. So here are the derived marginal latent state probabilities. So we can say that, like at state 1, very high probability to be using the first component model. Same with the first 5 or so states. Then there's a high probability of transitioning to the second state, then back up, and then up to 3. And there's a few of these states where there's some uncertainty whether or not we're in 1 or 2. There's one state where it's uncertain whether or not we're in 3 or 2. But overall, we get really strong inferences. Now, keep in mind that these are marginal, right? This is not a joint posterior here. So what we're looking at here are a bunch of marginal inferences that don't necessarily tell the whole picture, right? You can't trace through these to get a sense of what a trajectory is. If we want to look at trajectories, we need to look at samples. And we'll do that in just a second. So here are inferences for the initial probabilities, the elements of the transition matrices, and so on. Now, what happens if we use dynamical rescaling? And so here what we do is we keep the log, we compute a norm, we keep the log norm around, and then we normalize as we go. At the end, we're not just summing over the alpha, we're summing over the alpha plus all of these log norm terms that we've aggregated across each of the iterations. But otherwise, the calculation looks exactly the same. When we get to our generated quantities block, we do the Ford algorithm again, save all the intermediate results, and then we do the reverse algorithm. Again, we're going to rescale the betas, but you'll notice every time we use a beta, so for example here, we're normalizing the product of alpha times beta. Here again, and then where do we sample? Yeah, we compute R, and then we normalize that to get a lambda. So we're never really using the normalized betas. We're always using beta and then normalizing it. So the scaling that we're adding doesn't really change anything. So we don't have to worry about correcting for that later on. The fact that we're renormalizing in every state is already taking that into account, already correcting for that. And everything looks good, but more importantly, it looks exactly the same as what we had before, right? Everything looks pretty nice and consistent. Now, Stan has its own implementation of HMMs. I should know because I wrote the C++ for it. And so this is one reason why I know so much about these HMMs is I had to figure it out for this implementation. And so the nice thing about this is all we have to do is construct gamma, the transition matrix. We have to construct this big matrix of observational model outputs. And then we just plug it in and get one call. So the entire HMM is done in one line. All of the forward, backward, it's all done. When it comes to the generated quantities block, same thing. There's one function to generate the samples. There's one function to generate the latent probabilities. All done. Just one line. Just go. The only limitation about these functions here is that they assume a homogeneous transition probability. If you have a model with a heterogeneous transition probability, you can't use these built-ins. You're going to have to implement it yourself. So if we run this, not only is it simpler, it's using the C++ implementation of things. It's been highly tested. It's great. And we get the same results. So we check our kind of consistency for retrodictive behavior. Again, it's not just that it looks good in each model. They're exactly the same. Same here, and so on. right? So all of our inferences are consistent within the expected MCMC standard error, indicating these are all just 3 different implementations of the same model. And you can use whichever one is most useful for you. Now, while we're here, it's interesting to kind of consider, what is the benefit of an HMM? Why not just fit this to a static mixture model and ignore the fact that each observation can be coming from a separate data generating process? So let's try this again. Only instead of having a marginal model with all of these distinct but coupled assignment variables, we're going to have our kind of standard static mixture model marginal implementation. So now it's just this one set of component probabilities. And as I talk about in that mixture modeling chapter, we can interpret these lambdas as the probability that one of the data processes is responsible for all of the component observations, or the proportion of observations that are generated by each of the component data generating processes. To JD's comment, it's not that I was forced into it per se. It actually came up. So these HMMs come up a lot in practice, right? And it's just one of those things where it's not in every application, but in the applications where you need it, you need it. So I had a lot of applications that needed this, but I knew a lot of people that did. And then I'm trying to remember the order here, because originally what motivated this back in the day was that we had worked out, me and some colleagues, a way of doing auto diff on HMMs really efficiently. So if you're interested, you go to my writing page, go to the archive for all of my writing, and there's a chapter there called the discrete adjoint method. It's basically saying if you have a model whose output is defined implicitly as a kind of sequential or recursive update, how do you auto diff through that efficiently? And instead of just auto diffing through each step, is there a way of kind of constructing a direct solution that you can just implement explicitly? And this was all kind of in this research program for trying to understand how to do auto diff on implicit functions as efficiently as possible. We later generalized it so that it was even more powerful. But the first step we did was thinking about how to do auto diff for these discrete systems, and then later on it was for basically any implicit system, how to do it really efficiently. So it turns out you don't really get that much of a speed up over just auto diffing through the HMM directly. It's one of these things where the adjoint method isn't that much of a benefit. But we had figured out the gradients, and if you figured out how to do a gradient efficiently in auto diff for a function, it's a natural target for something like Stan. So we had done the math for the gradients. That then motivated doing the implementation, because we knew how to do it as efficiently as possible. And then it was like, okay, so we're going to do the implementation. How do we make sure we do it right? We have to make sure we understand the math and do everything, all the little details. And that was the first iteration through it. To be totally honest, the reason I wrote this chapter, it's been on my to-do list for the longest time. So I wrote the mixture modeling chapter last year, at the end of last year. It naturally sets up for this chapter. And in March, I was working with some colleagues, and they had an application that HMMs were perfect for. And so it was like, all right, I guess I should think about HMMs again. And that was that was the push, right? So the force to really write this chapter and understand HMMs, for the push to understand HMMs is more of a research thing, and then the push to write this chapter was a more of an application kind of a thing. So yeah, not important to anyone, but that's where these things come from. Okay, yeah, so we'll try the static mixture model. No problems fitting it because we have these distinct component models. Or in this case, you'll notice so the way you kind of break the exchangeability of these component normals. So they're all component normals, but the mu's are ordered, and that helps. That's enough to break the degeneracy. So it forces the first component to grab this kind of first bit in the data, the second component grabs that second bit in the data, and they can't switch because the ordering is enforced in the stand program. And again, that's discussed in the mixture modeling chapter. Now, if we look at our inferences for our component behaviors, our component observational model behaviors, we get some interesting results. So they're basically consistent with each other. For the first component model, mu1 and sigma1, basically the same, whether or not we run an HMM or we just collapse everything together and run a single mixture model. But when we look at mu2, sigma2, mu3, sigma3, we can see the benefit of the HMM. Even if we don't care about the latent dynamics of the latent states, we just care about the behavior of the observational models, we get stronger inferences by modeling the latent couplings and not assuming that they're independent or all the same. So we can take better advantage of the data, learn more about these behaviors by modeling those dynamics, if we do in fact think that they're reasonable. So there's always these two possibilities, right? And in fact, it kind of naturally motivates a ladder of complexity. You can always start with a static mixture model, and then if you start realizing that maybe there's some additional complexity there, maybe we want to start modeling the latent states and assume that there's some dynamics there, you can always go from the static mixture model to the HMM. And one nice thing about that progression is that by starting with a static mixture model, you can really spend your time thinking about the component observational models, making sure they're not exchangeable, making sure they're interpretable and things like that. Then you can add the coupling of the latent states in a later step. And you've already worked through the observational model structure, and you're now just adding just, this new piece to it. And that's, as I always recommend, you want to build your models sequentially. You want to not just jump to the most complicated model you can think of, add complexity a bit at a time. If you jump into an HMM with exchangeable observational models, it's going to explode in so many ways, it's really hard to figure out what's going on. If you do a static mixture model with exchangeable components, it's going to explode, but a little bit more of a manageable way where you can better identify what the problem is. And once you've fixed the observational models to be well behaved, then you can add the coupling of the latent states and transition to a hidden Markov model. Good pun there. And the only thing that can go wrong at that point is the degeneracy amongst the inferences for those latent states. Right? So just kind of piece by piece, we want to build our models up. All right, so in this case, you might notice that there's gaps in the data. So we have observations for a lot of the latent states, and then there's this big gap where there's a lot of unobserved latent states, and then a second big gap where there's unobserved latent states. So the simplest way of handling this, if we're assuming this data is missing at random, and it's not missing due to the behavior of any of our model parameters, then we can just... what am I going to do? Right, so I'm gonna construct this flag, this kind of auxiliary sequence that tells me whether or not there's an observation at every state. We can think of this as like that W array that I mentioned above, or that observed Markovian sequence that tells us whether or not there's an observation at every state. And then if we start off with zeros for our log omega, and then only if there's an observation do I update that with the component observational models. So there's going to be a lot of zeros in this log omega matrix corresponding to those gaps in the observations. The advantage of going this way is that I can use the stand built-in functions. So I can use exactly the same code as before and after. All I'm doing is changing the structure of that log omega input. So there's some autocorrelations here, a little bit higher than what we saw previously. Most of these are fine. The 50 is starting to get to the point where things like, meh, not great. But in some sense, not surprising because we have those big gaps in observations, right? There's not as much information constraining those behaviors, so there's going to be more uncertainty in the posterior, probably more complicated uncertainties, and that's harder for HMC to fit. Our retrodictive behavior looks good, both in terms of kind of the collapse, the marginal picture, and then the dynamics. And then we can look at our inferences for the latent states. And unsurprisingly, there's a lot of uncertainty between the gaps where there's no observations. So you can see the gaps here are kind of demarcated by the gray lines. And when there's data, in this first sequence here, we get pretty strong inferences. There's definitely more uncertainty than we had before, but there's less data than we had before. And then there's a lot of uncertainty. And so what's cool here is you can kind of see the kind of decay of the constraints of the latent states, or of the influence of the observed latent states. So right before we stopped getting any observations, all of the data to that point is helping to strongly inform what that latent state could be. And so it's saying the latent state, pretty confident latent state is 3. Now, when we start losing information, when we start getting into this gap where there's no observations, that constraint, like the persistence of the HMM, kind of keeps the probabilities close to 1/3. There's still probability of transitioning, right? Which is why it kind of immediately jumps. But you can see how that persistency is kind of decaying as we get down to about 5-10 steps in, and then it's pretty uniform. And then as we get closer to the edge of the window, we're getting the constraint from the state right after the edge of that window. So the state right edge where the observations come back is at 1, and so the probabilities kind of start slowly moving down towards that 1, right? So you're seeing that rigidity of the latent sequences, of the latent states, and that's what's helping inform what's going on here. And a similar kind of behavior here, just randomly, we have the same pattern where it's a 3 when there is observations, it's a 1 after the observations, and so there's this like slow shift of posterior probability away from 3 to more uniform, and then it concentrates back down towards 1 to match those boundary conditions. Anurag's asking about uncertainty. So it depends on which uncertainty you're talking about. The red ribbons here, these are nested posterior quantile intervals. So the light red is so each of these is computing the uncertainty of a different thing. Let's say here, in this figure here, each state, right, we get those marginal probabilities. So for the first state, I get 1,024 samples of Z-prob for that first state for each one of my chains. I can compute the 10% quantile and 90% quantile of those, average those across the 4 chains, and that gives me my light red. And then I do the 20 to 80, 30 to 70, 40 to 60, and 50, and then the median. And that gives me a way of kind of summarizing that behavior in a way that's nice to kind of connect together. So it's kind of a nice way of showing a lot of one-dimensional behaviors all at once. If you're interested in learning more about that, if you go to chapter 7 of the probability theory, and you go to section 5, characterizing one-dimensional push-forward distributions. This is very general, talking about just general probability theory and different ways of trying to kind of communicate these lower dimensional projections using histograms and CDFs and things like that. This is where you can kind of see this a little more formally how it's calculated. And then use Markov chain Monte Carlo to estimate what each of these quantiles are. So that's the kind of construction there. And then if you want to kind of learn more about the code and how it's done, if you go to my code page and go to the visualization tools, you can see both in R and Python, there's implementations of all these functions. And these aren't going to load, unfortunately. It's just going to, maybe the PDF will load. The HTML doesn't load, you have to download that locally. But you can see uses of these functions, and then you can look at the code to see how they're actually calculated. But yeah, that's the basic construction of those. I use these a lot. So the problem with looking at the Hessian of the log likelihood is, 1, it doesn't take the prior into account. 2, so the maximum likelihood has some nice properties to it. The maximum posterior density has less nice properties with it. That's because of the likelihood function is a function. Posterior density function is a density function. It transforms differently. It doesn't. There's a Jacobian involved. It gets all kind of nasty. So the mode of a posterior density is not as meaningful, interpretable as a mode of a likelihood function is. From a probability theory perspective, everything that we want to do is expectation values. So not point estimates, but expectations, things like means, quantiles, and the like. Again, if you're new to this, check out chapter 5 of the probability theory. This talks about expectation values, in particular. Where is that figure? Yeah, this figure here, about kind of this like conversation that you can have with your posterior. So there's various ways of using expectation values to try to visualize probabilistic behavior, and again, that's what that chapter 7 does, as it talks about using various expectation values to try to construct histograms, to construct these nested quantiles as a way of visualizing things. In the case of a normal, say your posterior is exactly normal, and it's one-dimensional, then going to the maximum of that posterior density, and then doing something like a Hessian at that point, or a second derivative, you can kind of extrapolate from that information, say what the quantiles will be. So instead of using MCMC to calculate them, you can just use that to get the same results. However, the second your posterior is not normal, there's any non-normality to it, the extrapolation of the posterior behavior from that point and then the gradient at that point can be arbitrarily off. So the challenge here is, how can you tell whether or not your posterior is normal enough for those kind of point approximations to be sufficiently good approximations to your posterior behavior? And the reality is you really can't. Right? Really, the only way to do it is to run something like MCMC to get this more comprehensive, more robust, more accurate picture of what's going on, and then double check and compare, but you've already run the MCMC at that point, so you might as well just use the MCMC. So aside from cases where you're using kind of a black box model where people have already validated that it's well behaved and has very, very normal posteriors to it, and you know that you're getting data that's very similar to the kind of data that model could have generated, in those kind of cases, variational approximations, point estimates, modal estimates, Hessians, those can all be useful. But when you don't know what your posterior looks like, which I would argue covers 99% of all applications, I'm going to go to a tool like MCMC, because I just don't know what it's going to look like. So these are much more robust visualizations and summaries, and that they will give you the same information when things are nice and super well behaved, but they're also going to give you the right interpretable information even when you don't have those normal posteriors. All right, so back to the exercises. Again, you can kind of see, again, I love this. It's just, you see that there's like the decay of that coupling, the kind of shift of probability from the last state it saw to the next state it sees. Just a cool little, everything works the way it's supposed to, right? It's just, math is great. Yeah, so I don't know, so yeah, I think like if you read like Jaynes, if you read Box back in the day, I love Box. Box is the absolute best, but they didn't have, you know, computers. We didn't have PCs the way we do now. So when you look at, you know, Box and Tao, for example, the really early Bayesian textbook, a lot of stuff they do is so ahead of its time, but in the end they still have to rely on analytic results because it's all they can do. So they do the best with it. They talk about how flat priors are approximating very diffuse priors, but then they validate their likelihoods are really narrow. They do all kinds of really nasty analytic calculations to get as much out of their models as they can, but they're still limited to that. With the advent of personal computing in the 80s, and really in the 90s with probabilistic programming tools like bugs, we were able to take Markov chain and Monte Carlo tools and really leverage them to be practical. So a lot of what I do, I really kind of think about it as like the work of George Box and I.J. Good, but with computers. So now that we have the computational methods that we can extract more accurate probabilistic information out of a posterior, how can we then implement these, you know, model building ideas and model validation ideas, but in a more mathematically sound way? and that's just kind of carrying over a lot of those ideas, but now using the more C word contemporary computational tools that have available to us. So yeah, one thing to be careful about with reading older literature is just recognizing what the limitations are and what they're, are they doing these calculations the way they are because it's the right way, or because it's the only way they could have done it at that time. So that let me come back to the end. I'll come back to the question there. That has more to do with about how hard it is to evaluate a model than it is about the MCMC. So I'll talk about the MCMC complexity in general a little bit, kind of towards. I'll just come back to it at the end. I just want to kind of finish things up here so that people can sneak out if needed. All right, so we were able to implement the missing data by just putting in zeros for the log omega matrix. The other way to do it is try to collapse the states. Now, the problem with the collapsing of the states is we get these inhomogeneous transition probability matrices, right? We know how to calculate it. We just have to, multiply those collapsed transition probabilities together. We just don't know how to do it with stands implementation. So in this case, we're going to have to use our own. So those earlier stand programs where we wrote our own forward and backward algorithms, that's why they're there. Is that if we need to do something with heterogeneous transition probabilities, we have the tools to do that. So I kind of do some tricks here to try to make this as efficient as possible. In particular, I have these deltas, which are kind of telling us how far apart the states are. And then I just go into a loop and I just multiply, by the gamma matrices appropriately. So instead of actually computing a collection of heterogeneous transition probability matrices first and then using those in the forward and backward algorithms, I just kind of do it dynamically, so I don't have to store all those probability matrices around. And the same thing in the reverse sweep. Where's the loop? Oh, sorry. So in the reverse sweep, then I'll do like the matrix power to multiply all those together to get this local transition matrix, and then do that. And the reason I have to do it this way is that you're not multiplying by gamma in the same way, right? It's not a matrix vector product anymore. It's now a row product. So you need calculate the full thing. You can't use the iterative approach anymore. Anyways, so that's just trying to be as efficient as possible. And I discuss some of the reasons why here. We get the same kind of autocorrelation, so this indicates that the implementation's not doing anything too distinct from what we had before. The retrodictive performance looks pretty similar, and you can see comparing them, we basically get equivalent inferences. There's a few small differences here and there. We can chalk that up to Markov chain Monte Carlo error, right? Just the numerical error for approximating our posterior behavior. Same with all of our inferences for the dynamics. Yes, and the mu's and the sigmas, right? So there are two approaches there. And again, you can see the trade-off. When you have these really long sequences of unobserved states with missing observations or no observations, then you get a much faster, like there's fewer states you have to iterate over if you collapse those states together, but then you have to do your own forward-backward implementation. If you just fill in those missing observations with zeros in the log omega matrix, then you can use Stan's built-ins. It's honestly not that much slower to do it that way, and you take advantage of the built-in tools. So I would say for most applications, you're probably just going to want to use the fact you can plug in zeros. If you get to a circumstance where computation is really, really limited, then you might want to consider this bespoke approach. All right, final example. So this is meant to demonstrate some of the challenges that you might encounter in an actual application of HMOs in practice. So we have our data here, right? And the idea is that there's some detector out in the woods somewhere, and it's observing things. It's counting the number of things it sees. It could be animals, it could be insects, it could be plants, whatever. And every month we get some data that tells us what, how many things that were seen in that interval of time. And we're interested in understanding whether or not we're in kind of in a high activity state or low activity state. So depending upon the ecology of the system, sometimes you might expect to see a lot of occurrences or a small number of occurrences. So we want to understand the behavior of these high and low activity states and the dynamics between them. How persistent are these states? How likely are you to transition from one to the other? So we have a pretty long data set over a few hundred months. And not everything is observed, right? So the other thing you might notice here is there's more observations than months. So we're going to, but if you look at the number of observations per state, you can see that some states have a lot of observations, say multiple detectors, but sometimes there's no observations. So we have a lot of annoyances here, right? There's heterogeneous number of observations per state that we're going to need to take into account. Now, if we look at the histogram of the observed data, kind of collapsing all the data on top of each other, independent of when it was collected, you can see there's this big peak at 0. You can see there's kind of this peak between 5 and 10. There's kind of a little bit of a tail coming out here. So there's definitely some interesting structure here. And you might imagine that this peak at 0 is the low activity state, and then this peak at between 5 and 10 is the high activity state. And we'll build the model to kind of go with that initially. We can also see the dynamics, where there's a lot of things are right at 0, and then there's kind of things that are bouncing around between 5 and 10. Again, we can kind of sort of maybe we're kind of seeing those different high and low activity states going on here. Now, the only kind of complication here is that because there can be multiple observations per state, if you look carefully, this isn't a trajectory. Right? Some of these states, there's multiple black lines, multiple dashes if we go up vertically. So to really kind of reduce this to a single trajectory, we have to reduce all those observations to a single value. And for that, I'm going to take an average. So for every one of the observations, we'll get rid of an average value, and then we'll have one average value per state. That might be missing if there's no data there. And that's something that we can then kind of think about as a trajectory that's cutting through across time. So for our initial model, we're going to use Poisson component observational models for the low and high activity states with 2 intensity parameters, lambda 1 and lambda 2, to capture the intensity of those states, of the what is high activity, what is low activity. You also notice there's a constraint on lambda 2, and this avoids the exchangeability problem. So it breaks exchangeability. So lambda 1 has to be the low activity, lambda 2 has to be the high activity. And then we build up our transition matrix. In this case, because it's just 2 by 2, there's only 2 values that we have to specify. So we can just specify those directly instead of dealing with simplex types. Put our priors down and run using our HMM functions. Right. So notice what I'm doing here is that we'll start the log omega column for the ice state at zeros, and then for every observation, we'll increment the model output, right? So if I have 5 observations, I want to have the product of all 5 of those model outputs in the overall model output, and then take the log, it turns into sums. So we're aggregating everything together, even though we have different numbers of observations in each state, not a problem. Everything is straightforward to encode into this log omega structure, right? That was really to help the point of this design of this particular HMM function, is that because we kind of abstract away this log omega matrix, you can do whatever you want on the observational model side. And you can still plug it in and use the built-in tools. The general quantities block looks basically the same to what we had in the first exercise. And everything looks good. No computational issues. But when it comes to retrodictive checks, we're starting to see it's not a great fit down here, right? We're underestimating what our model is under predicting what we see in the 0 counts. And then there's kind of the shoulder here that our model's getting. We're not getting the same kind of rapid drop that we see in the observed data. So something's not quite right with our model. It kind of looks like that the low activity Poisson really needs to be more of like either just a zero, like a delta at zero, or maybe like a zero inflated kind of a model, right? There's something else going on here. And we can see it more clearly if you zoom in, and you can again see that there's this kind of shoulder here in our predictions. Our posterior predictive distribution is a little bit too rigid, right? It's not decaying fast enough to match what we see in the observed data. Now, the dynamic retrodictive check is a little bit interesting, in that, so at the kind of higher counts, things look roughly okay, but if you zoom down towards zero, right, you can see that a lot of these data are exactly at zero, but our model doesn't want to predict exactly at zero, right? Our model predictions are between 0 and 1, or we're getting too much posterior probability at 1 and not enough at 0. And it'd be fine if this is happening for a few months, but the fact that it's happening over and over and over again suggests that we're missing something about that low activity behavior, or missing something about what's happening at 0 in particular. So this might be one of those cases where we're struggling, we identify there's an issue, we don't necessarily know what's going on with it until we go to a colleague who starts mentioning the fact that detectors are not really robust. That sometimes detectors break and no data is recorded. Not because no animals were seen, but because the detector just wasn't working at that site for that month. So now we have this really frustrating situation where there's another behavior we have to take into account. If the detectors are working, we can have these high and low activity behaviors that we observe. If the detector's not working, regardless of what the environment is doing, we're going to get a 0. Now the question here is, why is the detector breaking? Is it breaking at random? Is it breaking due to high activity? Like, is it breaking because it overflowed memory because it took too many pictures? Is it breaking because there's not enough power that was, is it breaking because it's solar powered and it kind of overloaded on power, but also because there's more sun that month, but also when there's more sun, there's higher activity of the environment we're looking at. Right? You can imagine all these things that could be happening that could require more subtle modeling. In this case, we're going to assume the detectors are breaking randomly. And the way we're going to model this is with a second latent sequence that has another binary sequence. It's 1, 2. 1 if the detector is working, and 2 if the detector is broken. And then I can tensor that detector sequence with the environment sequence. And that's going to give me these 4 tensor states. Working detector, low activity. Working detector, high activity. Broken detector, low activity. Broken detector, high activity. Our observational models will then be, if the detector is working, I'll have the low Poisson and the high Poisson. And if the detector is broken, I have the 0, like a Dirac at 0 in both cases. So I get the low activity model, high activity component observational model, Dirac observational model, Dirac observational model. Because the detector is breaking at random, and it's not, whether or not the detector breaks is independent of whether or not it was working in the previous month, our transition probability matrix looks pretty simple. It's just the same thing over again, because there's this one probability, independent of where we started. The reason another way you might think about tackling this is to have 3 states: high activity, low activity, broken detector. The reason I'm not doing that is that if the detector is broken, I still want to be able to infer whether or not there's low activity or high activity. So the advantage of this tensor approach is that not only do I infer what's happening with the detector, I can also infer what's happening with the activity. So if there's no observations or if there's 0 counts, because the detector was broken, I still can infer what's happening in terms of the environmental behavior. So putting this all together, we have our 4 states. They're ordered in a very careful way. We can construct our 2 transition matrices, one that depends on tau 1, and tau 2, and then the other depends on just tau d. And then I want to take the tensor product of the 2. right? So here's my gamma 2 for the environmental behaviors. This is just me implementing by hand a tensor product of matrices, following that calculation that I showed up above. And then for the observational model outputs, again, it's going to depend upon the which state we're looking at. So the first tensor state, working detector, low activity, we get the low activity Poisson. Second state is working detector, high environmental activity, so we get the higher Poisson. And the last two tensor states, broken detector, so regardless of what the environment is doing, we're getting no observations. We're getting 0 counts, which is giving us the log of 0 or minus infinity. We've played just the same game going backwards, but we can then use the same HMM latent RNG to generate our samples. So now we do this again, and our retrodict behavior is much, much nicer. So now our model is flexible enough to accommodate all of that behavior at 0 and the behavior between 5 and 10. Right? There's no shoulder anymore. We're right on top of the number of zeros. Everything's looking really much better now. And our dynamic behavior is much better. So if we look kind of close to 0, you can see that our posterior predictive distribution is now really close to 0 for a lot of these months. Every now and then you'll get some uncertainty, but it's not what we were seeing before, where it was just always uncertain between 0 and 1. Right now it's very certain that it's 0. That matches what we see in the observed data. So a much, much better fit overall, right? Much more adequate model. So now we're in a position to start making, looking at our inferences with the assumption that our model is adequate. We can look at the joint states, so the 1, 2, 3, 4. And, this is telling us two things, right? 1 and 2 is detectors working. 3, 4 is detectors broken. 1 is low environmental activity, 2 is high environmental activity. So we can look at the joint tensor states, or because it's a tensor product, I can just pick out the individual component states. So if I want to look at the environment, I can just look at the environment. And you can see sometimes we're very confident, sometimes there's a lot of uncertainty to what's going on, but we're quantifying all that uncertainty. We can also look at our inferences for the dynamics. So we have our initial state probabilities. We can also collapse this to probabilities for initial working detector, broken detector, high activity, low activity we wanted to as well. We have our transition probabilities. And the cool thing here is that we have the interpretability of those component transition probabilities. Right? So tau11 and tau22, these are isolated to the environmental persistency, whereas tau d is solely quantifying the behavior of the detector. So you can see here that the low activity state, it's kind of persistent, it's kind of sticky, but it's not that sticky, right? There's 50% chance you go from low activity to high activity. When you're in the high activity state, it's much stickier. It's harder to leave that high activity state. And then we get inferences for lambda 1 and lambda 2. Now, to see just how important it is to get an adequate model, we can do an inferential comparison. And you can see that our inferences for lambda 2 are pretty similar, but our inferences for lambda 1 are way off, right? If we don't incorporate the broken detector into our hidden Markov model, we get drastically underestimated inferences for lambda 1. And that's because, in that case, the low activity component is trying to capture both the low activity environment and the broken detectors. Now, a consequence of this is because the low activity component is trying to capture both of those things that have different dynamics, the inferred dynamics are also going to get messed up by this. In particular, we can see that the inferences for tau1 are much stronger than they should be, and our inferences for tau22, the kind of stickiness of the high activity state, is much lower than it should be. right? So what's happening here is that if you're in the high activity state, but the detector is broken, it looks like you're in the low activity state according to that first oversimplified model. So you don't see the stickiness or the persistency of that high activity state when you're not modeling the broken detector. It looks like you're just oscillating back and forth between them, when it's really what you're doing is oscillating between a working detector and a broken detector. But by modeling everything carefully, we can isolate those behaviors and get the inferences that we want. Right? That's one of the kind of key features of probabilistic modeling, is you model the entire data generating process, including all of the corruption, all of the contamination, so that you can isolate the thing that you care about in a well-posed way. I couldn't think of anything for the conclusion here. There's lots of other ways that you can generalize and extend HMMs. There's a lot of kind of like cool ways of using HMMs. For example, a lot of times people think of HMMs as these states are just being like constant time things. But then they have data that's collected across variable time intervals. And you can model that by having time as being one of your observations. And then your transition probabilities are more the probability of leaving a state. So it's kind of like a waiting time, almost a survival modeling kind of a thing. But it's all done within the HMM framework. But I don't know. It's one of those things that's like, it's so specific. It's really cool, but it's really kind of narrow and specific. It doesn't seem worth talk about for a general chapter. So I just kind of went with, just some blasé sentences there. But there's a lot of ways you can take this. And so there might be opportunities here for case studies and stuff going forwards. And then finally, there's a little appendix here on state space models in general. And the basic idea is that you can take all of the calculations that we did, and if you replace the sums with integrals, you get an immediate generalization, where your states are no longer discrete, but they're continuous. And this is where things like common filters come in, where your latent state isn't, which observational model you're generating data from. It's what is the position of an object, what is the velocity of an object, right? These more continuous variables, and you're modeling how not the assignment variable is changing across states. You're modeling how the position and velocity are changing across states. So the math is very similar. It's basically the same forward-backward algorithms. They're sometimes referred to as different things. This is where like filtering and smoothing become much more common terms. But the implementation, even though the math is pretty much the same, the implementation is much more difficult. Because now you have to keep track of these potentially arbitrary density functions, which isn't going to be practical in practice. So you're really limited to cases where these updates are all kind of closed within a certain family of density functions. And that way you can just keep track updates of the parameters, not the densities themselves. That's extremely exceptional. And really only happens with kind of linear dynamics and normals. And that's where we get things like the linear state space model, or otherwise known as the common filter. So this is a direction where, go back to the earlier discussion about, kind of like following analytic results. The common filter is like this extremely special case where you can do all of these calculations, but for continuous latent states. But that common filter is extremely rigid, and unless you're modeling dynamics that are happening over very, very short time intervals, it's not a very good model. And so you can try to, there are unscented common filters and non-linear common filters and all these kind of generalizations that try to break out of that linearity. But all of them are approximations and not technically consistent. They don't really define models, right? They're kind of approximate computation that can fall apart really easily. So from a modeling perspective, it's really hard to go beyond the common filter, and so it becomes kind of too narrow of a scope. And whereas the discrete HMMs, it's a much broader modeling technique that can be used over a much broader set of applications, and hence, worthy, in my opinion, of its own chapter. So with all that said, are there any questions about any of the material that we covered here at the end, or really across the entire chapter, about the forward-backward algorithms, the demonstrations, the implementation, anything like that? I'll give people a chance to think. In the meantime, I'll just very quickly get to Anurag's last question here. So the thing to keep in mind with Hamiltonian Monte Carlo in particular, as opposed to MCMC, I'm just going to refer to HMC specifically, the cost of HMC depends on three things. It depends on how expensive it is to evaluate a gradient, your model and its gradient. How many of those gradient evaluations you need per iteration, and then how many iterations you need. Usually, because HMC is kind of adaptive, we can fix the number of iterations. But what changes is the number of gradient evaluations we need per iteration. So now your two kind of levers on the cost are how long are your numerical trajectories, and how expensive is it to evaluate each step in those numerical trajectories. The number of gradient evaluations you need, the length of those numerical trajectories, depends on the complexity of your posterior uncertainties. The less normal and point-like your posterior is, the longer trajectories you need, the more expensive it's going to be. On the other side of things, how expensive it is to evaluate your model is going to depend on how much data you have, how complex the model is, and so on, right? So when you say something like, I have a 1,000,000 by 20,000 matrix, that's not an MCMC thing. That's a model evaluation thing, right? And that it could be really expensive to evaluate, say like a matrix vector product or something using that matrix to get it down to your final overall model output. But if you only need 10 of those gradient evaluations per iteration, and then maybe you cut down your iterations from the default of 1,000 to say 500, you can get it, that might be feasible to do in a day or two. You can also parallelize those evaluations so that, you can break that matrix up into 10 parts. And instead of doing one big matrix vector product, you can do a bunch of smaller matrix vector products that you can farm out over different machines. And that can speed things up quite dramatically, depending upon the I/O overhead and the like. So when it comes to optimizing performance and really determining whether or not MCMC or HMC in particular is a practical tool, you really have to consider each of those inputs. Is the bottleneck really the cost of evaluating your model, or is it the geometry of your posterior and how many model evaluations you need? If the bottleneck is the geometry, then you're going to get much more benefit out of adding more data, adding complementary data that reduces uncertainties, improving your prior modeling, and the like. If the bottleneck is the model evaluation, now this is more of a kind of local probabilistic programming problem, right? Like what can you do to speed up a matrix calculation in Stan or NumPy or JAX or whatever tool you're using. Blackjacks or there's a lot of these MCMC tools out there that allow you to write your model in different languages, and then use different auto differentiation techniques to evaluate them. So I've seen models that push up to that size. I have my favorite example. The biggest model I've ever seen had about 1 million parameters, and every evaluation wasn't just a matrix vector product. It was solving an n-body simulator. So it was literally solving the evolution of the early universe at every model evaluation. And my colleague at the time implemented this on a supercomputer. It was so gorgeous. Every posterior sample was a movie. It was so freaking cool. But you needed custom hardware for that, and that's always going to be kind of this conversation. So my preference in these modeling problems is to build a model that's appropriate to the problem, then determine how to work with that model efficiently. Can you do it on a laptop with a tool like Stan? Can you do it on a cluster with a tool like Stan? Do you have to use, can you do it on a cluster with a tool like Blackjacks because the Jacks, backend is easier for you to work with? Or you have to, write a custom MCMC sampler, custom HMC implementation so you can get down to the, just the cutting edge of performance for evaluating that model, right? But if you dump, a bunch of computation into doing a linear regression model to just make it bigger and bigger and bigger, if that linear regression model is not an appropriate model, for your system, if you have heavier tailed residuals, if you have confounding, right, then that really big linear regression model is not going to do anything. So it really is about those two levers to worry about, and then identifying the bottleneck, and then in my opinion emphasizing the model structure first, and then computation and optimization comes afterwards. Thanks, JD. Thanks for the comments earlier as well on the chapter. So as always, if there are any follow-up questions that people have after digesting this video, especially for those who are watching later on in the VODs, please feel free to drop them in the comments of the live stream post, or even the HMM original post. Any kind of feedback on organization, dumping some of the calculations into the appendix, or or being more clear about some of the wordings or anything like that, definitely don't hesitate to share. Always open to feedback. Worst case, I can just say no, right? But I really, really love the feedback and appreciate it. So please share early and often. Right. Coming up, there's I just did a post on some cute tricks with Choleskis and submatrices that might be of interest. And then I'm working on one of last month's questions. It's really next month's questions that I'll probably do as kind of a public post, because at this point it's going to be like a 10-page thing about survey modeling and weighted estimators versus weighted models. So that'll probably make public, or at least general for all Patreon supporters as opposed to the higher tiers as well. I've got a bunch of teaching coming up and the like, so I'm not quite sure what the next big writing project will be, but I'll keep everyone in touch. And we're due for another office hours, so I'll try to organize something like that for them, later on in the summer. So yeah, get all the questions together. Don't hesitate to share. Love the feedback as always. Thanks for the support. Honor, yeah, happy to have you here. Happy to answer all the questions I could. I hope it was useful. Thanks for engaging. Really appreciate it. Otherwise, happy modeling. And if you give this stuff a chance, let me know how it goes. Cheers.